Time had a birthday. 13.8 billion years ago, give or take 20 million years, the clock started. Not a clock sitting in space, not a timer counting down inside some cosmic waiting room. The clock itself. The thing that separates yesterday from tomorrow, cause from effect, memory from prediction. Before that moment, the word before had no meaning. There was no stage, no darkness, no empty room waiting to be filled. There was, in the most literal sense physics can muster, nothing. And then everything happened at once. This is not a metaphor. This is the conclusion of decades of observation, mathematics, and measurement. Satellites have mapped the afterglow. Telescopes have clocked the expansion. Particle accelerators have replicated the heat. And every single line of evidence points backward to the same impossible starting line. A point of infinite density and zero volume. A singularity where the laws of nature stop working and our most elegant equations curl up and die. Scientists call it the Big Bang. The internet calls it the beginning. And the truth is, after a century of refinement, no one can tell you what actually lit the fuse. This is not a gap we can close by looking harder. It is a boundary written into the fabric of reality itself, the Planck epoch. The first 10 to the minus 43 seconds, where space and time blur into something our physics cannot touch. But that has not stopped us from trying. Cosmic inflation, quantum fluctuations in a seething vacuum, collapsing universes that bounce instead of die. A multiverse where our Big Bang is just one spark in an eternal storm. These are not wild guesses, they are the cutting edge, and some of them suggest something even stranger, that nothing may be the most violent thing in existence. Welcome to Space Dust. If you're new here, please subscribe. We make these documentaries every day, and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. 13.8 billion years ago, the universe began. That sentence is 6 words long and it contains the entire history of everything you have ever known, everyone you have ever loved, every thought that has ever crossed your mind, every star in the night sky, every galaxy scattered across the cosmos, all of it compressed into a single statement about something that happened so long ago that human intuition gives up before it even tries to process the scale. 13.8 billion years. Say it out loud. Roll it around in your mouth for a second. Does it mean anything to you? It shouldn't. Your brain is not equipped to hold that number in any meaningful way. You can barely imagine 1,000 years. 1,000,000 is a ghost. 1,000,000,000 is functionally infinite. And we're talking about nearly 14 billion stacked end to end, stretching backward through time to a moment when there was no time, no space, no matter, no light, no atoms, no physics as we currently understand it. Just a beginning. Except that word beginning is doing far too much work. Because if something begins, that implies there was a state before it began. A blank page before the first word was written. A silence before the first note was played. But what does before mean when time itself has not started yet? What does it mean to ask what came before the Big Bang when the Big Bang is the event that created the conditions for before and after to exist in the first place? This is not a trick question. This is the central mystery of cosmology. And it is the kind of question that keeps theoretical physicists awake at night, scribbling equations on napkins, arguing in conference halls, publishing papers that contradict each other, and occasionally admitting in interviews that they have no idea what they are talking about. The Big Bang is the most successful scientific model we have for explaining where the universe came from. It is supported by mountains of evidence, the expansion of space, the cosmic microwave background radiation, the abundance of light elements like hydrogen and helium, the large-scale structure of galaxies, all of it fits. The math works. The observations match the predictions. For all practical purposes, the Big Bang is as close to a confirmed fact as science gets. And yet, for all its success, the Big Bang does not actually explain the beginning. It explains what happened after. It describes the universe's first few fractions of a second in extraordinary detail. It tells you how hot it was, how dense, how fast it was expanding. It tracks the formation of particles, the cooling of radiation, the moment when light first broke free and began racing across the infant cosmos. But the moment itself, the instant when everything switched from not existing to existing, that part remains stubbornly out of reach. The Big Bang theory starts the clock at a point when the universe is already there. Tiny, yes. Unimaginably hot and dense, absolutely. But there, present, real, a thing that exists and is expanding. The theory does not tell you where that thing came from. It does not explain what lit the fuse. It does not answer the question that every child asks the first time they hear about the Big Bang, and every adult still wonders about in the quiet moments before sleep. What caused it? Here is what we know with high confidence. About 13.8 billion years ago, give or take a few tens of millions of years, the universe as we observe it today was concentrated in a state of extreme density and temperature. Space itself was compressed to a scale so small that describing it in familiar terms is nearly impossible. Every point in the universe that is now separated by billions of light years was once packed together in a region smaller than the tip of a needle, smaller than an atom, smaller than a quark. Physicists call this initial state a singularity, though that word is less a description and more an admission of defeat. A singularity is what you get when the equations break down and start spitting out infinities. It is the mathematical equivalent of a shrug. From that unimaginably compressed state, the universe began expanding, not into something. There was no surrounding space for it to expand into. Space itself was expanding, carrying everything with it, stretching the fabric of reality outward in all directions at once. This is not an explosion in the traditional sense. The Big Bang was not a bomb going off in an empty room. It was the room itself coming into existence and growing larger. In the first tiny fraction of a second, something extraordinary happened. The universe did not just expand, it inflated. For a period lasting somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds, the universe grew faster than the speed of light. Not because anything was moving through space faster than light, that is still impossible, but because space itself was stretching at a rate that made the distance between any 2 points balloon outward faster than light could ever hope to cross. In that incomprehensibly brief instant, a region of space smaller than a proton expanded to something the size of a grapefruit. And that grapefruit-sized patch of space contained everything that would eventually become the observable universe. Every galaxy, every star, every planet, every atom in your body, all of it was there, packed into that grapefruit, which moments before had been smaller than the smallest thing you can imagine. This phase is called cosmic inflation, and it solved several major problems that had been bothering cosmologists for decades. It explained why the universe looks roughly the same in every direction. It explained why space is so flat on large scales. It explained where the tiny irregularities came from that eventually grew into galaxies and stars. Inflation was a brilliant idea proposed in the early 1980s, and it has held up remarkably well under scrutiny. But here is the part that matters for our purposes. Inflation tells you what happened in the first fraction of a second after the Big Bang. It does not tell you what caused the Big Bang. It pushes the question back one step, but it does not answer it. After inflation ended, the universe was still unimaginably hot and dense, but it was no longer inflating. It continued expanding at a more sedate pace, though still faster than anything we experience in daily life. The energy that drove inflation converted into matter and radiation, filling the universe with a seething plasma of particles. Quarks, electrons, photons, neutrinos, all smashing into each other at speeds and temperatures that would make the core of the sun look like a freezer. Over the next few 100,000 years, the universe cooled. Particles combined to form protons and neutrons. Protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium. Electrons eventually settled into orbit around those nuclei, forming the first true atoms. At that point, about 380,000 years after the Big Bang, the universe became transparent for the first time. Before that, it had been opaque, a fog of charged particles that scattered light in every direction. Once atoms formed, light could finally travel freely. The glow from that moment, redshifted by 13.8 billion years of expansion, is what we detect today as the cosmic microwave background. It is the oldest light in the universe, a faint whisper of radiation coming from every direction in the sky, and it is one of the strongest pieces of evidence we have that the Big Bang actually happened. From there, the story gets more familiar. Gravity pulled matter together into clumps. Those clumps became the first stars, which ignited and began fusing hydrogen into heavier elements. Stars clustered into galaxies. Galaxies clustered into groups and superclusters. Some stars exploded, seeding space with carbon, oxygen, iron, and all the other elements that make up planets and eventually life. Billions of years passed. Our solar system formed. Earth cooled. Life emerged. You were born. You're sitting here right now, listening to this, because of a chain of events that traces back to that initial moment 13.8 billion years ago. So far, so good. The problem is that none of this answers the original question. What started it? If the Big Bang was the beginning, what caused the beginning to begin? You might think the answer is obvious. Something must have caused it. That is how causation works. Every effect has a cause. Every event has something that came before it. Except that rule only applies inside the universe, where time exists and the laws of physics operate. At the moment of the Big Bang, time itself came into existence. The concept of before does not apply in the usual sense. Asking what came before the Big Bang is like asking what is north of the North Pole. The question feels like it should have an answer, but the framework you are using to ask it does not actually allow for one. This is where things get philosophically uncomfortable. We are built to think in terms of cause and effect. Our brains evolved to navigate a world where one thing leads to another, where pushing a rock makes it roll, where lighting a fire produces heat. The idea that something could simply begin with no prior cause, with no trigger, with no explanation beyond it just happened, is deeply unsatisfying. It feels like cheating. And yet, that might be the truth. Some physicists argue that the Big Bang does not need a cause because it represents the origin of causation itself. Time began at the Big Bang. Cause and effect began at the Big Bang. Asking what caused it is a category error, like asking what the colour of jealousy is. The question is grammatically correct but conceptually nonsensical. Others are not satisfied with that answer. They point out that the Big Bang theory, for all its success, is not a theory of creation. It is a theory of early expansion. It describes what happened after the universe was already there. It does not explain where the universe came from in the first place. And if you want to know where something came from, you need to look deeper, into the realm where physics as we know it stops working. That realm is called the Planck epoch, and it lasted for about 10 to the negative 43 seconds after the Big Bang. The Planck time, as it is known, is the smallest interval of time that has any meaning under current physics. It is the point at which quantum mechanics and general relativity, the two great pillars of modern physics, collide and produce nonsense. General relativity describes gravity and the large-scale structure of space-time. It works beautifully for planets, stars, galaxies, black holes, anything big. Quantum mechanics describes the behaviour of particles and forces at the smallest scales. It works beautifully for atoms, electrons, photons, anything tiny. The problem is that the two theories do not play nicely together. At the Planck scale, where the universe was smaller than 10 to the negative 35 metres and hotter than 10 to the 32 degrees, both theories are needed simultaneously. And when you try to combine them, the equations break. Infinities pop up. Predictions become meaningless. The math stops making sense. This is not a minor inconvenience. This is a fundamental barrier. We do not have a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single coherent picture. Without it, we cannot say anything definitive about what happened during the Planck epoch. We can speculate, we can build models, we can propose ideas, but we cannot test them. The first 10 to the negative 43 seconds of the universe's history are, for now, unknowable. That does not stop people from trying. There are several competing ideas about what might have happened before the Big Bang, or more accurately, what might have been going on during the Planck epoch that set the stage for the Big Bang. One idea is that the universe did not actually begin at the Big Bang. It might have been preceded by another state, another phase, a previous universe that collapsed and rebounded. This is called a cyclic or bouncing cosmology. In this picture, the Big Bang was not the absolute beginning. It was a transition point, a bounce, the moment when a contracting universe reached its smallest size and began expanding again. If this is true, then our universe might be just one cycle in an eternal sequence of expansions and contractions, each one giving birth to a new version of reality. Another idea involves quantum mechanics in a more direct way. At the quantum level, particles do not have definite states until they are observed. They exist in a superposition, a kind of probabilistic haze where all possible outcomes coexist at once. Some physicists have suggested that the universe itself might have started in a quantum state, a superposition of all possible configurations, and that the Big Bang was the moment when one particular outcome crystallized out of that haze. In this view, asking what caused the Big Bang is like asking why a particular quantum measurement gives a particular result. It does not. The outcome is probabilistic. The universe might have simply fluctuated into existence, a random quantum event with no deeper cause. There is also the possibility that the Big Bang was not a singular event, but one of many. The multiverse hypothesis suggests that our universe is just one bubble in a vast foam of universes, each one with its own Big Bang, its own laws of physics, its own history. In this scenario, Big Bangs are happening all the time, constantly, in different regions of a larger metaspace. Our universe is not special. It is just the one we happen to be in because, obviously, we could not be anywhere else. The multiverse is controversial. It makes predictions that are difficult or impossible to test, and some scientists argue that if a theory cannot be tested, it is not really science. Others counter that the multiverse arises naturally from certain well-tested theories, like inflation, and that dismissing it just because it is hard to observe is short-sighted. The debate is ongoing, and it is unlikely to be settled anytime soon. What all these ideas have in common is that they push the question back further without fully resolving it. If the universe bounced from a previous state, what started that state? If it fluctuated into existence from a quantum vacuum, where did the vacuum come from? If it is one bubble in a multiverse, what created the multiverse? Every answer leads to another question. Every explanation demands a deeper explanation. You can keep peeling back layers indefinitely and you will never hit bedrock. At some point, you either accept that there is no ultimate answer, that the chain of causation simply ends or loops back on itself, or you step outside the realm of science entirely and start talking about philosophy or theology. Science is comfortable saying we do not know. What it is less comfortable with is saying we cannot know, in principle, forever. But that might be where we are. The Planck epoch is a hard wall. Without a working theory of quantum gravity, we cannot see past it. And even if we develop such a theory, it is not clear that it would tell us what we want to know. It might just describe the rules that governed the earliest moments without explaining why those rules existed or where they came from. Here is a humbling thought. The entire observable universe, everything we can see with our most powerful telescopes, everything that light has had time to reach us from since the Big Bang, is only a small patch of the whole. The universe extends far beyond what we can observe. How far, we do not know. It might be infinite. If it is, then the Big Bang did not create the entire universe. It created the part of the universe we can see. The rest was already there, doing whatever it was doing before our local patch inflated and began expanding. That raises a strange possibility. Maybe the Big Bang was not the beginning of everything. Maybe it was just the beginning of us, our region of space, our laws of physics, our history. Somewhere else, far beyond the edge of the observable universe, there might be other regions with their own histories, their own Big Bangs, their own timelines. We would never know. They are too far away. Light from those regions will never reach us. The expansion of space ensures that the gap between us and them is growing faster than light can cross it. We are causally disconnected, two ships passing in an infinite ocean forever out of reach. If that is true, then the question of what caused the Big Bang becomes less a question about the origin of everything, and more a question about the origin of here, what caused our Big Bang, what set our clock ticking. What determined that this particular patch of space would inflate, cool, and eventually give rise to galaxies, stars, planets, and people? The answer might be nothing special. It might just be a random quantum fluctuation, a roll of the dice in a universe where dice are always being rolled. Or it might be something deeper, something we have not thought of yet, some mechanism or principle that we are still missing. The frustrating part is that we are asking the question from inside the system. We are part of the universe, made of the same stuff, governed by the same laws. We're trying to figure out where the whole thing came from, while standing on a tiny rock, orbiting an average star in an average galaxy in a universe we have barely begun to explore. It is like trying to understand the origin of a forest while you're an ant crawling on a single leaf. You can study the leaf, you can measure it, map it, analyze its structure, but the forest, the ecosystem, the larger context, all of that is beyond your reach. We are that ant, and the forest is the cosmos. And the question of what caused the Big Bang is the question of where the forest came from. We might never know, or we might be on the verge of figuring it out. The history of science is full of moments where problems that seemed insurmountable were suddenly solved by a new idea, a new tool, a new way of looking at the data. Quantum mechanics was invented because classical physics could not explain the behavior of atoms. General relativity was invented because Newtonian gravity could not explain the orbit of Mercury. The Big Bang theory itself was invented because static universe models could not explain the redshift of distant galaxies. Every time we hit a wall, someone finds a door. Maybe the same thing will happen here. Maybe someone working in a lab right now, or teaching a class, or lying awake at 3 in the morning with an idea that will not let them sleep, is about to crack the problem. Maybe the theory of quantum gravity is right around the corner. Maybe the next generation of telescopes will find evidence of a previous universe, or a multiverse, or something we have not even imagined yet. Or maybe not. Maybe this is the one question that stays unanswered. Maybe the origin of the universe is fundamentally unknowable, hidden behind a barrier that no amount of clever thinking or advanced technology can breach. That would be a strange place to end up. Humans are relentlessly curious. We do not like unsolved mysteries. We do not like being told there are questions we cannot answer. But the universe does not owe us answers. It does not care whether we understand it or not. It existed for more than 13 billion years before we showed up, and it will exist for trillions more after we are gone. We are a brief flicker in cosmic time, a momentary arrangement of atoms that happens to be capable of asking where it came from. The fact that we are asking at all is remarkable. The fact that we have gotten as far as we have, that we can trace the history of the universe back to the first fraction of a second, that we can measure the temperature of the early cosmos and map the distribution of galaxies across billions of light years, that we can say with confidence that the universe is 13.8 billion years old and expanding and cooling and full of dark matter and dark energy and stranger things we are still discovering. All of that is a staggering achievement. We should not take it for granted. But we also should not stop asking. Because the question of what caused the Big Bang is not just a scientific question, it is a human question. It is the same question our ancestors asked when they looked up at the stars and wondered where they came from. It is the question that drives every creation myth, every religious tradition, every philosophical inquiry into the nature of existence. It is the question that separates us from every other species on this planet. We do not just live in the universe. We want to know why there is a universe to live in. And that question, more than any answer we might find, is what makes us human. The singularity waits. Not in the past, not really, because the past ends where the singularity begins. But in the math, in the models, in the place where all our equations point and then fall silent. The singularity is not a place. It is not a moment. It is not a thing you could point to, even in principle, even if you had a time machine and a map of the early universe, and absolutely no regard for your own survival. The singularity is the word physicists use when their equations stop working and start screaming. It is the point where the math breaks down, where every variable you plug in returns infinity, where the rules that govern reality itself become meaningless. And according to general relativity, the singularity is where the universe began. That sentence should bother you. It bothers physicists. It has been bothering them for the better part of a century. Because if the universe started at a singularity, and a singularity is by definition a place where physics does not work, then physics cannot tell you what actually happened at the beginning. The most successful theory of gravity we have ever developed, a theory so precise it can predict the orbit of Mercury, down to the arc second, and describe the behaviour of black holes millions of light years away, throws up its hands at the exact moment you need it most. At the origin of everything, general relativity says, I have no idea what is going on here. Let's back up and define terms, because the word singularity gets thrown around casually and it deserves better. In mathematics, a singularity is a point where a function becomes undefined, or infinite. Divide by 0 and you get a singularity. Try to calculate the slope of a curve at a sharp corner and you hit a singularity. It is not that the answer is wrong, it is that there is no answer. The framework you're using to ask the question does not allow for one. In physics, Singularities show up in two main places. One is at the centre of a black hole, where all the mass that fell in gets compressed into a region of zero volume, and, according to the equations, infinite density. The other is at the beginning of the universe, where all the matter and energy that now fills billions of light-years of space was once compressed into that same impossible state. Infinite density, zero volume, a point that contains everything and occupies nothing. Your brain is trying to picture this right now and failing. That is fine. It should fail. The singularity is not something that can be visualized in any meaningful way because it violates every intuition you have about how objects behave. You cannot compress something into zero volume. Volume is a measure of space, and zero space means no space, which means there is nowhere for the thing to be. And yet the math insists it is there, or was there, or exists in some tense that does not map onto normal language. Here is how we ended up with this problem. In 1915, Albert Einstein published his general theory of relativity, and it changed everything. Before Einstein, gravity was a force. Objects with mass pulled on each other across empty space, and nobody knew why. Isaac Newton had written down the equations for how strong that pull was, and they worked beautifully for predicting the motion of planets and moons and falling apples. But Newton himself admitted he had no idea what gravity actually was. He called it action at a distance and left it at that. Einstein had a different idea. Gravity, he said, is not a force, it is geometry. Mass and energy warp the fabric of space and time, bending it the way a bowling ball bends a trampoline. Objects moving through that warped space follow curved paths, and we perceive that curvature as gravity. The Earth is not being pulled toward the Sun by some invisible force. It is travelling in a straight line through space that has been bent by the Sun's mass. From the Earth's perspective, it is moving straight. From our perspective, watching from outside, it looks like an orbit. The math behind this idea is ferociously complicated. General relativity is written in the language of differential geometry, a branch of mathematics that most people never encounter unless they specifically go looking for it. The core equation, the Einstein field equation, relates the curvature of space-time to the distribution of matter and energy within it. On one side of the equation, you have geometry. On the other side, you have stuff. The equation tells you how stuff bends space and how bent space tells stuff how to move. Solving the Einstein field equation for realistic situations is hard. Really hard. Most of the time you need a computer, but in certain simple cases you can solve it by hand, and one of those cases is a universe that is homogeneous and isotropic. Homogeneous means it looks the same at every point. Isotropic means it looks the same in every direction. Obviously the real universe is not perfectly smooth. There are galaxies, voids, clusters, all kinds of structure. But on the larger scales, averaged over billions of light years, the universe is surprisingly uniform. Matter is spread out fairly evenly. The cosmic microwave background looks the same no matter where you point your telescope. The universe, in the big picture, is homogeneous and isotropic enough that you can treat it that way and get useful answers. In the 1920s, a Russian physicist named Alexander Friedmann applied general relativity to a homogeneous, isotropic universe, and derived a set of equations describing how such a universe would evolve over time. The Friedmann equations, as they are now called, predict that a universe filled with matter and energy cannot stay static. It has to be either expanding or contracting. Space itself has to be changing size. At the time, this was a shocking result. Einstein himself initially resisted it. He had assumed the universe was eternal and unchanging, and he had even added an extra term to his equations, the cosmological constant, to force a static solution. When observations later confirmed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder. Whether he actually said that is disputed, but the story has stuck because it makes a good point. The math was telling him something true about reality, and he ignored it because it did not match his intuition. The Friedmann equations describe an expanding universe, but they also do something else. If you run them backward in time, they describe a contracting universe. And if you keep running them backward, the universe gets smaller and smaller, denser and denser, hotter and hotter, until you hit a point where the equations stop making sense. That point is the singularity. Here is what the math says. Take the scale factor, the variable that describes how big the universe is at any given time. Right now, that scale factor is increasing. The universe is expanding. Galaxies are moving apart. Space is stretching. If you reverse time, the scale factor decreases. The universe gets smaller. Keep going, and the scale factor approaches zero. At zero, the entire universe, all of space, all of matter, all of energy, is compressed into a single point. The density becomes infinite. The temperature becomes infinite. The curvature of space-time becomes infinite. Every quantity you try to calculate blows up. Physicists call this the initial singularity, and it sits at the very beginning of the Friedman models. It is not something that happens inside the universe. It is the boundary of the universe's history. Time starts there. Space starts there. Before the singularity, the concept of before does not even apply because time has not started yet. This sounds like a philosophical problem, and it is, but it's also a physics problem. A theory that predicts infinities is a theory that has broken down. Infinity is not a number you can measure. It is not a state you can describe. It is a sign that you are asking questions your equations are not equipped to answer. When general relativity predicts a singularity at the beginning of the universe, it is not telling you what the universe was actually like at that moment. It is telling you that general relativity itself stops being valid there. The same thing happens with black holes. When a massive star collapses at the end of its life, general relativity predicts that all the matter gets compressed into a singularity at the centre. Infinite density, zero volume, all the usual nonsense. But nobody seriously believes there is an actual point of infinite density sitting inside every black hole. What they believe is that general relativity is incomplete. It works beautifully outside the event horizon, in the region where space-time is curved but not catastrophically so. Inside the horizon, where the curvature becomes extreme, something else has to take over. Some deeper theory, some more complete description of gravity that does not break down when densities get too high. The leading candidate for that deeper theory is quantum gravity, a framework that would unify general relativity with quantum mechanics. We will get to that in a moment. For now, the point is that singularities are not features of reality. They are bugs in our models. They are places where the map stops, not because the territory ends, but because the map is inadequate. So what does it actually mean to say the universe started at a singularity? It means that if you take general relativity seriously and run the clock backward, you eventually hit a wall. You reach a state so extreme that the theory can no longer describe it. That state is often characterized by three quantities, all of which become problematic at the singularity: infinite density, zero volume, and infinite temperature. Infinite density is the easiest to explain. Density is mass divided by volume. If you compress a fixed amount of mass into a smaller and smaller volume, the density goes up. Compress it into zero volume and the density becomes infinite. The entire mass of the observable universe, something like 10 to the 53 kilograms, crammed into a space with zero size. That is what the Friedman equations predict at the singularity. Zero volume is harder to wrap your head around. Volume is a measure of space. An object with zero volume does not occupy any space. It is not small. It is not tiny. It is dimensionless, a point in the mathematical sense. And yet, according to the model, all of space was once that point, not located at that point. Was that point? Space itself had zero size. There was no elsewhere for the universe to be. The singularity was not sitting in the middle of an empty void. It was everything. Infinite temperature is the consequence of compressing energy into a vanishingly small space. Temperature is related to the kinetic energy of particles. The more energy packed into a given volume, the higher the temperature. At the singularity, the energy density becomes infinite, and so does the temperature. There is no upper limit. The early universe, even a tiny fraction of a second after the singularity, was hotter than anything you can create in a lab. Hotter than the core of any star, hotter than the inside of a supernova. And the singularity itself, if you could even call it itself, was infinitely hotter still. None of these quantities are physically meaningful. You cannot measure infinity. You cannot observe zero volume. These are not descriptions of reality. They are artifacts of pushing a mathematical model past its breaking point. And that brings us to the real question. If general relativity cannot describe the singularity, what can? The answer, if we had one, would involve quantum mechanics. Quantum mechanics is the other great pillar of modern physics, and it governs the behaviour of the very small. Atoms, electrons, photons, quarks, all the fundamental particles and forces, they all obey the rules of quantum mechanics. Those rules are strange. Particles exist in superpositions of multiple states until they are measured. They can tunnel through barriers that classical physics says they should not be able to cross. They are described not by definite positions and velocities, but by probability distributions, wave functions that tell you the likelihood of finding a particle in a given state. General relativity, on the other hand, governs the behaviour of the very large. Planets, stars, galaxies, black holes, the large-scale structure of space-time. It is a classical theory, meaning it does not include quantum effects. It treats space-time as a smooth, continuous fabric. You can zoom in as far as you like and space-time still looks smooth. There is no graininess, no discreteness, no uncertainty. For most purposes, this is fine. Quantum effects are negligible at large scales, and relativistic effects are negligible at small scales. You can use quantum mechanics to describe atoms and general relativity to describe galaxies, and the two theories never need to talk to each other. But at the singularity, both theories are needed simultaneously. The entire universe is compressed into a region so small that quantum effects dominate. The curvature of space-time is so extreme that relativistic effects dominate. You need a theory that incorporates both. You need quantum gravity. We do not have one. Not a complete one, anyway. There are several candidates: string theory, loop quantum gravity, causal dynamical triangulations, asymptotically safe gravity, others, but none of them are fully developed, and none of them have been tested experimentally. Building a theory of quantum gravity is one of the great unsolved problems in physics. It has been unsolved for decades, and it might remain unsolved for decades more. The reason it's so hard is that quantum mechanics and general relativity are built on fundamentally different assumptions. Quantum mechanics is probabilistic. General relativity is deterministic. Quantum mechanics treats time as an absolute background parameter. General relativity treats time as part of the space-time fabric that can stretch and warp. Quantum mechanics works with discrete particles and fields. General relativity works with smooth geometry. Trying to merge these two frameworks is like trying to write a sentence that is simultaneously in English and Mandarin. The grammar does not line up, and yet somewhere in the overlap there has to be an answer. Because the singularity is a quantum gravity problem. It is a place where space-time is so violently curved and so microscopically small that both quantum mechanics and general relativity are needed to describe it. Whatever actually happened at the beginning of the universe, it happened in a regime where our current theories do not apply. We can make guesses. We can build models. We can extrapolate from what we know about quantum mechanics and what we know about gravity and try to sketch out what a unified theory might look like. But we cannot say, with confidence, what was actually going on. This is where the Planck epoch comes in. The Planck epoch is the earliest period of time that has any theoretical meaning under current physics. It is not the singularity itself. It is the moment immediately after, if after even makes sense, when the universe was still unimaginably hot and dense, but no longer in a state of total mathematical breakdown. The Planck epoch is defined by the Planck time, which is approximately 10 to the negative 43 seconds. That is 0.000, 42 more zeros, 1 seconds. It is the smallest interval of time for which the concept of time as we understand it is thought to be meaningful. The Planck time is derived from three fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. Combine them in the right way and you get a timescale. That timescale, 10 to the negative 43 seconds, is the natural unit of time in a theory of quantum gravity. Below that scale, space-time itself might not be continuous. It might be grainy, discrete, foamy, structured in some way we do not yet understand. Asking what happened before the Planck time might be like asking what happened north of the North Pole. The question assumes a framework that does not apply. At the Planck epoch, the universe was about 10 to the negative 35 meters across. That is the Planck length, the natural unit of distance in quantum gravity. For comparison, a proton is about 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than that. It is so small that there is no known physical process that could probe it. Our most powerful particle accelerators smash protons together at energies high enough to probe scales of about 10 to the negative 18 meters. To reach the Planck scale, you would need an accelerator the size of the galaxy. The temperature at the Planck epoch was roughly 10 to the 32 degrees Kelvin. That is the Planck temperature, the natural unit of temperature in quantum gravity. For comparison, the core of the Sun is about 15 million degrees. The temperature at the centre of a nuclear explosion is about 100 million degrees. The Planck temperature is 10 to the 32, a 1 followed by 32 zeros. There is no physical analogy for it because nothing that hot has existed in the observable universe since the Planck epoch itself. At those temperatures and densities, the four fundamental forces, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, might not have been distinct. They might have been unified into a single force. This is speculation based on theories like grand unification and string theory, but the basic idea is that at high enough energies, the differences between forces wash out, and they behave as different aspects of one underlying interaction. If that is true, then the Planck epoch was not just the earliest moment of time, it was a moment when the laws of physics themselves were different. The rules that govern the universe today, the separation of forces, the existence of distinct particles, the flow of causality, all of that might have emerged only after the Planck epoch ended. This is where things get philosophically uncomfortable again. If the laws of physics were different during the Planck epoch, then explaining what happened during the Planck epoch requires laws we do not have. You are trying to describe a system using rules that only apply after the system has evolved past the point you are trying to describe. It is circular, it is frustrating, and it is where we are. The Planck epoch lasted, if that word even applies, for about 10 to the negative 43 seconds. Then something happened. The universe transitioned out of the Planck regime and into a state that general relativity can at least approximately describe. The temperature dropped. Though dropped is a misleading word because it was still incomprehensibly hot, around 10 to the 28 degrees. The universe was still smaller than an atom, but it was no longer in the quantum gravity regime. It was in the domain where our equations start working again. What caused that transition? Nobody knows. Some models propose that the singularity was not actually a singularity, that quantum effects prevented the universe from collapsing all the way to zero volume and instead caused it to bounce. In these bouncing cosmologies, the Big Bang was not the beginning. It was a rebound from a previous contracting phase. The universe might have been cycling through expansions and contractions for eternity, with each bounce resetting the clock and erasing the memory of what came before. Other models suggest that the singularity is real, but that it represents a boundary of space-time rather than a point in space-time. In this view, asking what happened before the Big Bang is not just hard to answer, it is meaningless. Time itself began at the singularity. There was no before. The question does not compute. Still, other models propose that the universe emerged from a quantum fluctuation in a pre-existing space, a kind of vacuum that is not empty but seething with quantum activity. In this picture, universes are constantly popping into existence, most of them collapsing back into nothing almost instantly, but a few, like ours, inflating and surviving. The Big Bang was not the creation of everything. It was the creation of our bubble. All of these ideas are speculative. None of them have been tested, none of them may be testable. The Planck epoch is so far removed from anything we can observe directly that it might remain forever beyond the reach of experiment. We can build models, we can make predictions, we can look for indirect signatures in the cosmic microwave background or in the distribution of galaxies. But we cannot go back and watch the Planck epoch unfold. We cannot run the experiment again. That does not mean the question is hopeless. Science has a way of finding answers to questions that seem unanswerable. Before quantum mechanics, the structure of the atom was a mystery. Before general relativity, the orbit of Mercury was an anomaly. Before the Big Bang theory, the expansion of the universe was unexpected. Each time, someone found a way forward. A new idea, a new tool, a new way of looking at the data. The singularity problem is the same kind of challenge. It is hard, yes. It might take decades to solve, or longer, but it is not unsolvable in principle. A theory of quantum gravity would resolve the singularity by replacing it with something more physically reasonable, a bounce, a quantum state, some kind of smooth transition that avoids the infinities. We do not know what that something is yet. But the fact that general relativity predicts a singularity does not mean there was actually a singularity. It means there was something general relativity cannot describe. The search for quantum gravity is ongoing. Thousands of physicists around the world are working on it, writing papers, testing ideas, building mathematical frameworks. String theory proposes that the fundamental constituents of reality are not particles but tiny vibrating strings, and that space-time itself emerges from the interactions of these strings. Loop quantum gravity proposes that space-time is not continuous but made of discrete chunks, loops of gravitational field woven together into a network. Both approaches are elegant, both are incomplete, both might be wrong. And here is the humbling part. Even if we develop a working theory of quantum gravity, even if we can describe the Planck epoch in detail, we still might not know what caused the Big Bang. Quantum gravity would tell us what the universe was like at the earliest moments. It would not necessarily tell us why those moments happened in the first place. It would replace one mystery with another, pushing the question back one more step without fully resolving it. But that is how science works. You do not solve everything at once. You solve one piece, and that opens up the next piece. The singularity is the piece we are stuck on right now. It is the wall we cannot see past. And on the other side of that wall is the Planck epoch, a sliver of time so brief and so extreme that it barely qualifies as time at all. A moment when the universe was hotter, denser, and stranger than anything we have words for. A moment when the rules had not yet been written. A moment that might hold the answer to everything if we can ever figure out how to look at it. For now, the singularity sits at the edge of our models like a locked door. We know it is there. We can describe the room on this side of it. We can measure the temperature, the density, the rate of expansion, everything that happened after the door opened. But the door itself, the moment it opened, the reason it was ever closed in the first place, all of that is still out of reach. And it will stay out of reach until we find the key. That key is quantum gravity, and the search for it is one of the great intellectual adventures of our time. Right behind that locked door, in the first unimaginable fraction of a second after the universe began, something else was happening. Something that took a universe the size of a grain of sand and turned it into a universe the size of a galaxy, all in less time than it takes light to cross the width of a single atom. Right behind that locked door, in the first unimaginable fraction of a second after the universe began, something else was happening. Something that took a universe the size of a grain of sand and turned it into a universe the size of a galaxy, all in less time than it takes light to cross the width of a single atom. That something is called cosmic inflation. And if you have heard of it before, chances are you have heard it described as the moment the universe exploded. That description is not quite right. Explosions happen in space. Debris flies outward through a pre-existing void. Inflation was not an explosion. It was something stranger. It was space itself growing so fast that the word far stops making sense. It was not matter rushing away from a center point. It was the distance between any 2 points stretching, doubling, doubling again, doubling over and over so many times in such a short span that the numbers involved feel less like physics and more like a typo. Here is the scale we're talking about. During a period lasting somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26. Some models push that number to 10 to the 60. Let's stick with the conservative estimate for now, 10 to the 26. That is a 1 followed by 26 zeros. A region of space smaller than a proton, something on the order of 10 to the negative 26 meters across, grew to roughly 1 meter in 10 to the negative 35 seconds. If that does not sound impressive, let me put it differently. If you could inflate a human cell at that same rate, it would grow larger than the observable universe. If you inflated a grain of sand, it would engulf multiple galaxies. If you inflated a period at the end of a sentence, it would stretch past the orbit of Jupiter before you finish blinking. Inflation did not just make the universe bigger, it made it incomprehensibly bigger, in a stretch of time so brief that calling it a moment is generous. And the wild part, the part that still makes physicists pause when they talk about it, is that inflation was not optional. It was not some exotic side effect or rare event. It was, according to the models, a necessary phase in the early universe. Without it, the universe we see today, the flat, smooth, homogeneous cosmos full of galaxies and stars and people asking questions, would not exist. Something else would be here instead. Something inconsistent with the observations. Something wrong. To understand why inflation had to happen, you need to understand the problems it solved. Because inflation was not invented as a fun idea. It was invented because cosmologists in the late 1970s were staring at their data and realizing that the standard Big Bang model, as elegant and successful as it was, had some serious gaps. 3 problems in particular kept coming up, and none of them had satisfying answers. They were called the flatness problem, the horizon problem, and the monopole problem. Inflation solved all 3 in one stroke. That is why it became one of the most important ideas in modern cosmology. Not because it was obvious, but because it worked. Let's start with the flatness problem, because it is the easiest to visualize. The universe, on the larger scales, appears to be geometrically flat. That does not mean it is two-dimensional. It means that the rules of Euclidean geometry apply. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. Light travels in straight lines unless something bends it. This is not obvious. General relativity allows for 3 possible geometries. The universe could be flat, like an infinite sheet of paper. It could be positively curved, like the surface of a sphere, where parallel lines eventually converge. Or it could be negatively curved, like a saddle, where parallel lines diverge. Which geometry you get depends on the total density of matter and energy in the universe. If the density is exactly equal to a value called the critical density, the universe is flat. If the density is higher, the universe curves positively and will eventually stop expanding and collapse back in on itself. If the density is lower, the universe curves negatively and will expand forever, accelerating as it goes. Measuring the density of the universe is hard, but by the late 1990s, observations of the cosmic microwave background and distant supernovae had pinned it down. The universe is flat, or so close to flat that any curvature is undetectable within our measurement precision. The density matches the critical density to within about 1%. That is strange. Not because flat universes are impossible, but because flatness is unstable. If the universe starts out even slightly curved, that curvature grows over time. A universe that is 1% denser than critical early on becomes many times denser than critical later. A universe that is 1% less dense becomes vastly less dense. Flatness is a knife edge. To have a universe that is still flat today, more than 13 billion years after the Big Bang, the density in the early universe had to be fine-tuned to an absurd degree. We're talking about a difference of 1 part in 10 to the 60. That is not a typo. 1 part in 10 to the 60. If the density had been off by more than that, even by a tiny amount, the universe would have either collapsed within seconds or spread out so fast that no structures could ever form. Why would the universe start out so perfectly balanced? There is no reason in the standard Big Bang model, you just have to assume it did. You have to write into your initial conditions that the density was exactly, almost impossibly, precisely tuned to the critical value. And that feels like cheating. It feels like you are putting in the answer you want to get out. This is the flatness problem. Not that the universe is flat, but that the Big Bang model gives no explanation for why it is flat. It just is, and you are supposed to accept that. For a while, physicists did accept it. They did not love it, but they did not have a better option. Then, in 1980, a young physicist named Alan Guth had an idea. Guth was working on a completely different problem at the time. He was trying to figure out why we do not see magnetic monopoles, hypothetical particles predicted by certain theories of particle physics that should have been created in huge numbers in the early universe. The monopole problem was a real headache, and Guth was exploring whether a brief period of rapid expansion could dilute the monopole density enough to explain their absence. While running through the math, he realized that the same rapid expansion would solve the flatness problem as well. Here is how. Imagine you are standing on the surface of a balloon. From your perspective, the surface curves. You can see it bending away from you in every direction. Now start inflating the balloon. As it gets bigger, the curvature decreases. The surface looks flatter and flatter from your local perspective. Keep inflating it until the balloon is the size of the Earth. Now the curvature is so slight that you cannot detect it without sensitive instruments. Inflate it to the size of the solar system and the surface looks perfectly flat no matter how carefully you measure. Inflate it to the size of a galaxy, and flatness is not just a good approximation, it is effectively exact. That is what inflation does to the universe. Whatever curvature existed before inflation, the exponential expansion stretches it out until it is undetectable. You do not need to fine-tune the initial conditions. You do not need to assume the universe started flat. Inflation makes it flat, no matter what it was before. The knife edge problem disappears. Any initial density, any initial curvature, gets smoothed out by the sheer violence of the expansion. By the time inflation ends, the universe is flat to within a part in 10 to the 60 or better, and it stays flat as it continues expanding at a more sedate pace. Guth wrote up his idea, titled it with the wonderfully understated name A Possible Solution to the Horizon and Flatness Problems, and presented it at a seminar in January 1981. The reaction was immediate. Within months, other physicists were building on the idea, refining it, testing it against observations. Inflation went from a speculative fix to a cornerstone of cosmology faster than almost any idea in the history of the field. The second problem inflation solved, the horizon problem, is even more puzzling. The cosmic microwave background, the faint glow of radiation left over from the early universe, looks almost exactly the same in every direction. The temperature varies by only about 1 part in 100,000 from place to place. That uniformity is remarkable, and it needs an explanation. Why is the universe so smooth? The obvious answer is that different regions of the universe were in contact with each other early on, exchanging energy and heat until they reached equilibrium. That is how things equalize in everyday life. Leave a hot cup of coffee on a table and it cools to room temperature because heat flows from the coffee to the surrounding air. The universe could have done the same thing. Regions that were hotter would have radiated energy to regions that were cooler, evening things out. Except there is a problem. For regions to exchange energy, they need to be in causal contact. Light, or some other signal, needs to have had time to travel from one region to the other. And in the standard Big Bang model, vast sections of the observable universe were never in causal contact. They were too far apart. Light from one region could not have reached the other, even if it had been travelling since the beginning of time. This is the horizon problem. When we look at the cosmic microwave background, we are seeing light that has been travelling toward us for more than 13 billion years. That light comes from a shell surrounding us, a surface at a fixed distance in every direction. The light from one edge of that shell, say the part of the sky above the North Pole, comes from a region of space that is now billions of light years away from the region, producing the light we see above the South Pole. In the standard Big Bang model, those two regions were never close enough to communicate. They were always separated by a distance greater than light could have travelled. So how did they end up at the same temperature? You could argue that they just started out at the same temperature, that the universe was born uniform. But that brings you back to the same problem as the flatness issue. You're putting in the answer by hand. You are assuming the initial conditions were exactly right to give you the result you observe, and you have no explanation for why the initial conditions were that way. It is unsatisfying. It smells like a coincidence. And physicists hate coincidences. Inflation solves the horizon problem by making those distant regions not so distant after all. Before inflation, the entire observable universe, all the space that would eventually grow into billions of light years of cosmos, was packed into a region far smaller than an atom. That tiny patch was small enough that light could easily cross it. It was causally connected. Different parts of it could exchange energy and reach equilibrium. Then inflation happened. That tiny, smooth, uniform patch got stretched by a factor of 10 to the 26 or more. Regions that had been next-door neighbours were suddenly separated by vast distances. But they remembered their shared history. They stayed at the same temperature because they had been at the same temperature before inflation blew them apart. Think of it like a photograph. Take a picture of a smooth surface, say a white wall with a consistent texture. Now blow up that photograph to the size of a billboard. The texture is still uniform because it came from a single original image. Inflation did the same thing to the universe. It took a small, smooth patch and stretched it to cosmic proportions. The smoothness we see in the cosmic microwave background is not a coincidence. It is the direct result of the observable universe starting out small enough for light to smooth it out before inflation took over. Both the flatness problem and the horizon problem point to the same underlying issue. The standard Big Bang model works beautifully for describing the universe after the first fraction of a second. but it requires a set of initial conditions that seem impossibly fine-tuned. Inflation removes that fine-tuning. It provides a mechanism, a physical process that naturally produces the flat, smooth universe we observe. You do not need to assume anything special about the starting conditions. You just need inflation. So what is inflation really? What causes it? The answer, or at least the best answer we have, involves something called the inflaton field. This is a hypothetical scalar field, a kind of energy field that permeates all of space. Scalar just means it has a magnitude but no direction, unlike a vector field like the electromagnetic field. The inflaton field has not been directly detected. We do not know what it is made of or how it fits into the standard model of particle physics, but its properties can be inferred from the role it plays in the inflationary model. The key feature of the inflaton field is its potential energy curve. In physics, a field has a potential, a function that describes how much energy the field has at different values. Think of it like a landscape. A ball sitting on a hill has potential energy because it can roll down. The inflaton field works the same way, except the landscape is mathematical rather than physical. During inflation, the inflaton field is sitting near the top of its potential, in a region that is very flat. Not zero, not at the peak, just in a flat stretch where the potential changes very slowly. When a field sits in a region of nearly constant potential, it does something strange. Instead of behaving like ordinary matter or radiation, it acts like a kind of negative pressure, a repulsive force that drives space apart. This is similar to dark energy, the mysterious force currently accelerating the expansion of the universe, except much, much stronger. The inflaton field, stuck in its flat potential, generates a huge amount of negative pressure, and that pressure causes space to expand exponentially, not linearly, exponentially. The size of the universe doubles, then doubles again, then doubles again, over and over, in a runaway process that only stops when the inflaton field finally rolls down its potential and settles into a lower energy state. The exact details of the inflaton potential are still debated. Different models propose different shapes, different energy scales, different durations for inflation. But the basic picture is the same. You need a field with a nearly flat potential. The flatness is crucial. If the potential is too steep, the field rolls down too quickly, and inflation ends before it has time to solve the flatness and horizon problems. If the potential is perfectly flat, inflation never ends, and the universe just keeps expanding forever, which is also a problem because then structure never forms. You need just the right shape. Flat enough to sustain inflation for a sufficient period, but not so flat that it never stops. How long did inflation last? The answer depends on how much expansion you need to solve the problems. Cosmologists talk about something called e-folds, a measure of how many times the universe doubled in size. Each e-fold represents an expansion by a factor of e, the base of the natural logarithm, about 2.7. To solve the flatness problem, you need roughly 60 e-folds. That means the universe expanded by a factor of e to the 60th power, which is about 10 to the 26. 60 doublings, more or less, in the span of 10 to the negative 35 seconds or so. That time frame is so short it barely registers as time. Light, the fastest thing in the universe, travels about 300 million meters per second. In 10 to the negative 35 seconds, light moves about 3 times 10 to the negative 27 meters. That is a tiny fraction of the width of a proton. During the time it would take light to cross a proton, the universe was expanding by a factor large enough to turn a subatomic speck into a region the size of a galaxy or larger, depending on the model. And here is where the story gets even stranger. Inflation was not just fast, it was faster than light in a very specific sense. Nothing can move through space faster than light. That is a rule, one of the firmest rules in physics, but space itself can expand faster than light. There is no speed limit on the expansion of space. During inflation, regions of the universe that were initially close together were carried apart so quickly that the distance between them grew faster than light could travel. An observer in one region, if such a thing could exist, would see neighbouring regions receding at speeds greater than the speed of light. Not because anything was moving through space, but because space itself was stretching. This is not a violation of relativity. Relativity says that nothing can move through space faster than light. It says nothing about how fast space itself can expand. The distinction is subtle but important. Objects moving through space carry information, and that information cannot travel faster than light. The expansion of space does not carry information. It just changes the distance between things. During inflation, the distance between any 2 points in space was growing exponentially, and that growth was, in many regions, faster than light. The observable universe today, the region of space we can see with our telescopes, all of it originated from a tiny patch that was smaller than an atom. That patch inflated so fast that parts of it are now separated by distances that light has not had time to cross, even after nearly 14 billion years. The end of inflation is as important as the beginning. Inflation could not last forever. If it did, the universe would be empty, cold, and boring. Fortunately, the inflaton field eventually reached the bottom of its potential, and the exponential expansion stopped. When the field settled into its lowest energy state, all that potential energy had to go somewhere and converted into particles. The inflaton field decayed, releasing its energy in the form of matter and radiation, filling the universe with a hot, dense plasma. This process is called reheating, and it is the transition from the inflationary epoch to the more familiar hot Big Bang phase. After reheating, the universe continued expanding, but at a much slower rate, no more doubling every fraction of a second. Now the expansion was governed by the ordinary dynamics of matter and radiation, following the Friedmann equations. The universe cooled. Particles combined to form atoms. The cosmic microwave background was released. Stars and galaxies formed. You know the rest. Inflation set the stage for all of it. The evidence for inflation comes from several sources, but the most compelling is the cosmic microwave background itself. Inflation makes specific predictions about the properties of the CMB. It predicts that the temperature fluctuation should follow a particular statistical pattern, a pattern determined by quantum fluctuations in the inflaton field during the inflationary period. Those quantum fluctuations, tiny random variations in the density of the field, got stretched to cosmic scales by inflation. After inflation ended, they became the seeds for structure formation, the tiny overdense and underdense regions that eventually grew into galaxies and clusters. The pattern of temperature fluctuations in the CMB, as measured by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite, matches the predictions of inflation remarkably well. The fluctuations are nearly scale invariant, meaning they have roughly the same amplitude at all sizes, and they follow a Gaussian distribution, meaning their statistical properties are those of random noise. Both of these features are natural consequences of inflation. They are much harder to explain without it. Inflation also predicts that the universe should be flat, and observations confirm this. The total density of matter and energy in the universe is equal to the critical density to within about 1%. That is exactly what inflation predicts. No fine-tuning required. Inflation also predicts that the universe should be homogeneous and isotropic on large scales, meaning it should look the same in all directions and all locations, averaged over large enough distances. Again, observations agree. There is another prediction, one that has not yet been confirmed but that cosmologists are actively searching for. Inflation should have generated gravitational waves, ripples in space-time itself during the period of exponential expansion. These primordial gravitational waves would have left a faint imprint on the cosmic microwave background, a pattern of polarization in the light that is distinct from the temperature fluctuations. Detecting this signal, called B-mode polarization, would be direct evidence of inflation. Several experiments are currently looking for it. So far, no detection, but the search continues. For all its success, inflation is still a framework rather than a single specific theory. There are dozens of different inflationary models, each proposing different shapes for the inflaton potential, different energy scales, different durations. Some models have the inflaton field rolling slowly down a smooth hill. Others have it navigating a more complex landscape with bumps and valleys. Some models involve a single inflaton field. Others involve multiple fields interacting with each other. The observational data is good enough to rule out some models and favour others, but not good enough to pin down one definitive version of inflation. There is also the question of what caused inflation to start in the first place. If the inflaton field was sitting at the top of its potential, why was it there? What set it in motion? This is the same kind of question as asking what caused the Big Bang, and it has the same kind of answer. We do not know. Some models propose that the inflaton field started in a high-energy state as a natural consequence of the Planck epoch, the period of quantum gravity that preceded inflation. Others suggest that inflation is eternal, that it is always happening somewhere in the larger multiverse, and that our observable universe is just one bubble that emerged from an eternally inflating background. In that picture, asking what started inflation is like asking what started time. The question does not have an answer because inflation has always been happening. This brings us to one of the most provocative implications of inflation. If inflation happened once, it might still be happening elsewhere. The models that describe inflation, particularly the ones involving a nearly flat potential, tend to be eternal. Once the inflaton field starts inflating space, it keeps inflating in some regions while stopping in others. Where it stops, you get a bubble universe like ours, filled with matter and radiation. Where it keeps going, space continues expanding exponentially, and within that expanding space, new bubbles can form. Each bubble is a separate universe with its own Big Bang, its own laws of physics, its own history. This is the inflationary multiverse, and it is one of the most controversial ideas in cosmology. Critics argue that it is not science because the other universes are forever beyond our reach. We cannot observe them, cannot test their existence, cannot gather data about them. Proponents argue that the multiverse is a natural prediction of inflation, and that dismissing it just because it is hard to test is short-sighted. The debate is ongoing, and it is not going to be settled anytime soon. What is not debated, at least not seriously, is that inflation happened. The evidence is too strong, the problems it solves are too real, the predictions it makes match the observations too well. Inflation is as close to a confirmed part of the cosmic story as you can get without actually travelling back in time and watching it happen. And yet, for all its explanatory power, inflation does not tell you where the universe came from. It tells you what happened in the first fraction of a second, how a tiny patch of space grew into the vast cosmos we see today. It tells you why the universe is flat and smooth and full of structure, but it does not tell you why there was a tiny patch of space to begin with. It does not explain the singularity. It does not answer the question of what came before. What inflation does is push that question further back. Instead of asking why the Big Bang happened, you are now asking why inflation happened. And the answer to that question, if it exists, lies even deeper in the physics of the early universe. It lies in the realm of quantum mechanics, where particles pop into existence from nothing, where cause and effect blur together, where the very concept of something and nothing starts to lose meaning. That is where we need to go next. Into the quantum foam, into the probabilistic haze that underlies reality itself, into the strange and counterintuitive world where universes might not need a cause at all. Into the quantum foam, into the probabilistic haze that underlies reality itself, into the strange and counterintuitive world where universes might not need a cause at all. Because if inflation tells us how the universe got big, quantum mechanics might tell us where it came from in the first place. Not from something, not from an already existing lump of matter waiting to explode, but from nothing. Or at least from what looks like nothing, until you examine it closely enough to realize that nothing is not what you thought it was. This is going to sound insane. It should sound insane. But the physics behind it is some of the most rigorously tested and confirmed science humanity has ever developed. Quantum mechanics is not a guess. It is not a philosophical thought experiment. It is the operating manual for the universe at its smallest scales, and it has been checked and rechecked in labs all over the world for more than a century. Every computer you have ever used, every LED light, every smartphone, every solar panel, every piece of modern technology that involves electrons or photons or any kind of subatomic particle, all of it works because quantum mechanics is correct. The predictions it makes are so precise that in some cases they match experimental results to 1 part in a billion, and those same predictions, those same equations, tell you something deeply weird about empty space. They tell you that empty space is not empty. At all. Ever. It is seething with activity. Particles flicker into existence and vanish again in spans of time so short that you cannot directly observe them. Energy appears from nowhere, borrows itself into being for a fraction of a second, and then pays itself back before the universe notices. The vacuum, the space between particles, the so-called nothing that fills most of the cosmos, is actually a bubbling, roiling quantum foam of activity that never stops. And it is that foam, those fluctuations, that might have given birth to everything. Let's start with what quantum mechanics actually says, because the popular version of it, the one that shows up in bad science fiction and worse philosophy, is a mess. Quantum mechanics does not say that reality is subjective. It does not say that consciousness creates the universe. It does not give you permission to believe whatever you want about how the world works. What it does say is that at very small scales, the behaviour of particles is fundamentally probabilistic. You cannot predict exactly where an electron will be or what it will do. You can only calculate the probability of finding it in a particular state when you measure it. Before the measurement, the electron exists in a superposition, a blend of all possible states, weighted by their probabilities. Measure it, and the superposition collapses into one definite outcome. This is not because we lack information. It is not because our instruments are not good enough. It is a feature of reality. Particles at the quantum level do not have definite properties until those properties are measured. Position, momentum, energy, spin, all of these quantities are fuzzy, probabilistic, undefined in the strict sense until something forces them to pick a value. And the universe, it turns out, is built on this fuzziness. Everything's solid. Every table and chair and planet and star is made of particles that are individually fuzzy. It is only when you pile trillions of them together that the fuzziness averages out and you get something that looks solid and predictable. One consequence of this fuzziness is the Heisenberg uncertainty principle, which you have probably heard of. The principle says that there are pairs of properties, like position and momentum, or energy and time, that cannot both be known precisely at the same moment. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of measurement tools, it is a limitation of reality. The universe itself does not allow certain pairs of quantities to be simultaneously well defined. The version of the uncertainty principle that matters for our purposes is the one involving energy and time. It says that if you look at a very small region of space for a very short period of time, the energy in that region is uncertain. It fluctuates. For a brief moment, energy can appear that was not there before, as long as it disappears again quickly enough that the average energy over a longer time period stays constant. The shorter the time interval, the larger the possible fluctuation. This is not a violation of energy conservation. Energy is still conserved on average, over longer timescales, but on very short timescales, it can spike up or down, borrowing energy from the vacuum and paying it back before the books need to balance. These fluctuations are not hypothetical. They have measurable effects. One of the most famous is the Casimir effect, discovered in 1948 by Dutch physicist Hendrik Casimir. Take two uncharged metal plates and place them very close together in a vacuum, a few micrometers apart. Quantum mechanics predicts that the plates should feel a tiny attractive force pulling them together. The reason is that the space between the plates suppresses certain wavelengths of virtual particles, the particle-antiparticle pairs that pop in and out of existence in the vacuum. Outside the plates, all wavelengths are allowed. Inside, only certain wavelengths fit. The difference in vacuum energy creates a pressure imbalance, and the plates are pushed together. This has been measured in labs. The force is tiny, but it is real, and it matches the predictions of quantum field theory to high precision. Another effect is the Lamb shift, a tiny difference in the energy levels of electrons in a hydrogen atom. According to the simplest version of quantum mechanics, certain energy levels should be identical. But when you account for the interaction between the electron and the fluctuating electromagnetic field of the vacuum, those levels split slightly. The Lamb shift was measured in 1947 by Willis Lamb, and it provided some of the earliest direct evidence that the quantum vacuum is not empty. The electron is constantly interacting with virtual photons, particles of light that pop into existence for a moment and then disappear. Those interactions change the electron's energy in a way that can be calculated and observed. So when physicists talk about the quantum vacuum, they are not talking about empty space in the everyday sense. They are talking about a space filled with fields, with fluctuations, with temporary particles that exist for fractions of a second before annihilating back into the void. These are called virtual particles, though that name is a bit misleading. They are not particles in the sense that you can grab one and put it in a box. They are better thought of as ripples in the underlying quantum fields, disturbances that briefly borrow energy from the vacuum and then collapse back. But they have real effects. They contribute to forces, they shift energy levels, they can be detected indirectly through their influence on other particles. Now take that picture, that quantum foam of fluctuations, and apply it to the early universe. During the inflationary epoch, space was expanding exponentially. The inflaton field was driving that expansion, stretching space so fast that quantum fluctuations in the field were being pulled apart before they could collapse back. Normally, a quantum fluctuation in a field appears and disappears in a tiny fraction of a second. But during inflation, space was expanding faster than the fluctuations could decay. A fluctuation that started out smaller than an atom could be stretched to the size of a galaxy before it had time to vanish. And once it was stretched that far, it stopped being a quantum fluctuation and became a classical perturbation, a real, lasting ripple in the energy density of the universe. This is how inflation converts quantum fuzziness into cosmic structure. The tiny random variations in the inflaton field, driven by quantum uncertainty, got blown up to macroscopic scales by the exponential expansion. After inflation ended and the inflaton field decayed into particles, those perturbations became variations in the density of matter and radiation. Regions that had slightly more energy than average became the seeds for galaxy clusters. Regions with slightly less energy became voids. The entire large-scale structure of the universe, every galaxy, every cluster, every supercluster, traces back to quantum fluctuations that existed for a fraction of a second during inflation and then got frozen in by the expansion of space. The evidence for this is written across the sky in the cosmic microwave background. The CMB is not perfectly uniform. It has tiny temperature variations, about 1 part in 100,000, that correspond to density variations in the early universe. Those variations follow a very specific statistical pattern. They are nearly Gaussian, meaning their distribution looks like random noise, and they are nearly scale invariant, meaning they have roughly the same amplitude at all sizes. Both of these features are natural predictions of quantum fluctuations during inflation. If you start with a quantum field, calculate how its fluctuations evolve during an inflationary expansion, and then work out what pattern those fluctuations would leave in the CMB, you get exactly the pattern we observe. This is one of the great triumphs of modern cosmology. Observations from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured the temperature fluctuations in the CMB to extraordinary precision, and the data matches the predictions of inflationary quantum fluctuations almost perfectly. The amplitude is right, the shape of the power spectrum is right, the statistical properties are right. There are small deviations, anomalies that are still being investigated, but the overall agreement is stunning. The largest structures in the universe, spanning hundreds of millions of light-years, began as quantum blips smaller than a proton. Think about that for a second. The galaxy cluster you can see through a telescope containing thousands of galaxies and trillions of stars started as a random quantum fluctuation in a field that existed for less than a billionth of a trillionth of a trillionth of a second. It was not planned. It was not designed. It was a roll of the quantum dice, a probabilistic hiccup in the fabric of space that got amplified by inflation into something real and lasting. You're living on a planet that orbits a star that formed inside a galaxy that exists because of a quantum fluctuation. Your entire cosmic address traces back to a random event that had no cause, no reason, no purpose beyond the fact that quantum mechanics allows it to happen. This brings us to the deeper question. If quantum fluctuations can create structure, can they create the universe itself? Can the entire cosmos, not just the variations within it but the whole thing, emerge from a quantum fluctuation in the vacuum? The answer depends on what you mean by vacuum and what you mean by nothing. In quantum field theory, the vacuum is the lowest energy state of a system. It is the state where no particles are present, but the fields are still there, humming along at their minimum energy. That minimum energy is not zero. This is another consequence of the uncertainty principle. If a field had exactly zero energy, you would know both its value and its rate of change precisely, which the uncertainty principle forbids. So even the vacuum state has some energy, called the zero-point energy, or vacuum energy. That energy is real, and it has real effects like the Casimir effect. But here is the twist: the vacuum state is not unique. In theories with multiple fields or complex potentials, There can be more than one vacuum, more than one low-energy state that the fields can settle into. Some of these vacua might be stable, meaning once the field gets there, it stays there. Others might be metastable, meaning they are stable for a while but could eventually decay into a lower energy state. And some vacua might have very different properties, different masses for particles, different strengths for forces, different laws of physics. If the universe started in a high-energy vacuum, a false vacuum as it is sometimes called, it could have tunneled quantum mechanically into a lower energy state. That tunneling process would release energy, a lot of energy, and that energy could drive inflation. In this picture, the Big Bang was not the beginning of everything. It was a phase transition, a moment when the universe jumped from one quantum state to another. The tunneling event created a bubble of space, our universe, inside a larger background that might still be in the high-energy state. Outside the bubble, if there is an outside, space might be doing something completely different. This is one version of how the universe could emerge from a quantum fluctuation. The fluctuation is not a particle popping into existence. It is a tunneling event, a rare but allowed quantum process where the fields that fill space jump from one state to another. The probability of such an event is extremely low, but in an infinite amount of time, or in a space that is large enough, even extremely low probability events eventually happen. And once the tunneling occurs, the energy released by the transition drives inflation, and you get a universe. The math behind this is based on a framework called quantum cosmology, which tries to apply the rules of quantum mechanics to the universe as a whole. The most famous proposal in this area is the no-boundary proposal, developed by Stephen Hawking and James Hartle in the 1980s. Their idea was that the universe does not have a beginning in the usual sense. Instead, time itself emerges smoothly from a quantum state where the distinction between time and space breaks down. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes a framework that does not apply. Time does not extend backward past the Big Bang because time itself started there, or more accurately, time emerged from a timeless quantum state. The no-boundary proposal is elegant, but it is also highly speculative. It requires a theory of quantum gravity, which we do not have in complete form. It makes predictions that are hard to test, and it is not the only proposal. Other physicists have suggested different ways of thinking about the quantum origin of the universe. Some models propose that the universe is eternal at the quantum level, constantly fluctuating between different states, with big bangs happening all the time in different regions. Others suggest that the universe emerged from a collision of higher dimensional brains, objects from string theory that exist in more than 3 spatial dimensions. The landscape of ideas is vast and no single model has won out. What all these models have in common is the idea that the universe did not need a traditional cause. In classical physics, every event has a cause. Push a ball and it rolls. Heat water and it boils. There is a chain of causation stretching back through time. But in quantum mechanics, that chain can be broken. Quantum events are fundamentally probabilistic. A particle can decay without anything causing it to decay at that particular moment. It just happens, with a probability determined by the laws of quantum mechanics. The same thing could be true for the universe. It might not have been caused by anything. It might have just happened, a quantum event with no deeper explanation beyond the fact that the laws of quantum mechanics allowed it. This is philosophically unsettling. Humans are wired to look for causes. We want to know why. The idea that the universe might not have a why, that it might just be a brute fact, a random quantum fluctuation that happened to succeed, goes against every instinct we have. But the universe does not care about our instincts. It does what the laws of physics allow, and the laws of quantum mechanics allow for events without causes. There is a wrinkle, though. Quantum fluctuations in the vacuum still assume that the vacuum exists. The quantum fields need to be there, humming along, ready to fluctuate. The laws of quantum mechanics need to be there, defining what fluctuations are allowed. So even if the universe emerged from a quantum fluctuation, you still have not explained where the quantum fields came from, or where the laws came from, or why there is something rather than nothing. You have pushed the question back one step, but you have not answered it. Some physicists argue that this is as far as physics can go. The laws of quantum mechanics, the existence of fields, the framework of reality itself, these might be brute facts that cannot be explained. They just are, and the universe exists because they exist. Others are not satisfied with that answer. They point out that quantum field theory assumes a background, a space-time in which the fields live and fluctuate. But at the very beginning there might not have been a background. There might have been no space-time, no geometry, no stage for the fields to perform on. What you need is not just quantum mechanics, but a theory of quantum gravity, a framework that describes how space-time itself emerges from something more fundamental. This is where the idea of quantum foam comes in. In some approaches to quantum gravity, space-time at the smallest scales, the Planck scale, is not smooth. It is grainy, foamy, chaotic. The familiar notions of distance and time break down. Space and time might not even be fundamental. They might emerge from some deeper structure, a network of quantum information or a web of entangled states. In this picture, the Big Bang was not an event that happened in space-time. It was the moment when space-time itself crystallized out of a pre-geometric quantum state. The trouble is that we do not have a fully worked out theory of quantum gravity. We have proposals, frameworks, partial models, but nothing complete. String theory is one candidate. It suggests that the fundamental building blocks of reality are not particles but tiny vibrating strings, and that space-time emerges from the interactions of these strings. Loop quantum gravity is another candidate. It proposes that space-time is made of discrete loops of gravitational field, woven together into a network. Both approaches have their strengths and weaknesses, and neither has been conclusively tested. Without a theory of quantum gravity, we cannot say for certain what happened at the very beginning. We can sketch out possibilities, we can build models, we can make educated guesses, but we cannot claim to know. The Planck epoch, the first 10 to the negative 43 seconds after the Big Bang, remains a mystery. And the question of what came before, if before even makes sense, is still open. What we can say is that quantum fluctuations played a crucial role in shaping the universe. They seeded the structure we see today. They turned a smooth, featureless expanse of space into a cosmos full of galaxies and stars and planets. They did this not because they were special, not because they were guided by some plan, but because they were inevitable. Quantum mechanics demands fluctuations. You cannot have a quantum field without them, and if inflation happened, and the evidence strongly suggests it did, then those fluctuations got amplified into the large-scale structure of the universe. The cosmic microwave background is the smoking gun. The temperature variations we see in the CMB, those tiny 1 part in 100,000 ripples, are a direct snapshot of the quantum fluctuations that existed at the end of inflation. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into hydrogen atoms. Before that moment, the universe was opaque, a fog of charged particles that scattered light in every direction. After that moment, light could travel freely. The CMB is the light from that transition, stretched and redshifted by 13.8 billion years of expansion. And imprinted on that light is the pattern of density variations that existed back then, which in turn reflects the pattern of quantum fluctuations from the inflationary epoch. Satellites have mapped that pattern in exquisite detail. The Cosmic Background Explorer, launched in 1989, detected the fluctuations for the first time. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured them with high precision. The Planck satellite, launched in 2009, pushed the measurements to their current limits. The data from these missions has been analysed, cross-checked and squeezed for every bit of information it contains, and the conclusion is clear. The fluctuations match the predictions of quantum mechanics applied to an inflationary universe. The amplitude is right. The spectrum is right. The statistical properties are right. There are some puzzles. The CMB has a few anomalies, features that do not quite fit the simplest models. There is a slight asymmetry between the northern and southern hemispheres of the sky. There is a cold spot, a region that is slightly colder than the surrounding areas, that is larger than expected. These anomalies might be statistical flukes, or they might be hints of new physics. But they do not change the overall picture. The quantum fluctuation model works. It explains the data. It makes predictions that have been confirmed. One of the most striking predictions is the near-scale invariance of the fluctuations. In simple terms, this means that the size of the fluctuations does not depend strongly on the scale you are looking at. Small-scale fluctuations have roughly the same amplitude as large-scale fluctuations. This is exactly what you expect from quantum fluctuations during inflation. The reason is that all scales were once subatomic. Every patch of the universe, no matter how large it is today, was once smaller than an atom. The quantum fluctuations that seeded each patch were all roughly the same size, because they all came from the same quantum field in the same state. Inflation stretched them to different sizes, but the underlying amplitude stayed the same. This prediction is generic to inflation, and has been confirmed by the CMB data to high precision. Another prediction is that the fluctuations should be Gaussian, meaning their statistical distribution should follow a bell curve. This is a property of random processes, and quantum fluctuations are fundamentally random. If the fluctuations were non-Gaussian, it would suggest some kind of nonlinear process or interaction during inflation. The data shows that the fluctuations are very close to Gaussian, with only small deviations. Those deviations are interesting, and they are being studied, but the overall Gaussian nature is clear. This is another point in favour of the quantum fluctuation model. So the picture that emerges is this. The universe began, or at least our observable patch of it began, in a state dominated by the inflaton field. That field was sitting in a region of nearly constant potential, generating a huge amount of negative pressure that drove exponential expansion. During that expansion, the inflaton field was subject to quantum fluctuations, tiny random variations in its value from point to point. Those fluctuations were stretched by inflation to macroscopic scales. When inflation ended, the inflaton field decayed into particles, and the fluctuations became variations in the density of matter and radiation. Over time, gravity amplified those variations, pulling matter together in the overdense regions and emptying out the underdense regions. The overdense regions became the seeds for galaxies. The underdense regions became voids, the cosmic web of structure that we see today, the filaments and clusters and superclusters, all of it grew from those quantum seeds. This is not speculation. This is the standard model of cosmology, backed by decades of observations and refined through countless calculations and simulations. The quantum origin of structure is as well established as any idea in modern physics. The only thing that is not well established is what caused the quantum fluctuations to exist in the first place, or why the inflaton field was there, or what set the whole process in motion. Those are the deeper questions, and they remain open. One way to think about it is that quantum fluctuations do not need a cause. They are built into the fabric of quantum mechanics. Any field left to its own devices will fluctuate. It cannot not fluctuate. The uncertainty principle guarantees it. So if the inflaton field existed, it had to fluctuate. And if it was driving inflation, those fluctuations had to be stretched and amplified. The structure of the universe is not a miracle. It is an inevitable consequence of the laws of physics applied to a field undergoing exponential expansion. But that still does not explain why the inflaton field existed, or why the laws of quantum mechanics are what they are, or why there is a universe for those laws to apply to. You can keep peeling back the layers, and you will always find another question. This is the nature of the problem. Every answer leads to a new question, and the chain never ends. Or maybe it does end, but not in the way we expect. Maybe the universe is one of many, a single bubble in an infinite foam of universes, each one with its own set of quantum fluctuations, its own history, its own laws. In that picture, asking why our universe has the properties it does is like asking why you were born in the city you were born in. It is not that there is a deep reason. It is just that there are many cities, and you had to be born in one of them. Our universe has the properties it does because those are the properties that allow it to exist long enough and in a stable enough form to produce observers who can ask the question. Other universes, with different properties, might not be so lucky. They might collapse too quickly, or expand too fast, or never form stars, or never develop the kind of chemistry that leads to life. We are here because we are in a universe that allows us to be here. The anthropic principle, as it is called, is not an explanation. It is an observation. But it might be the only observation we can make if the multiverse is real. The multiverse is controversial. It pushes the limits of what we can test and what we can know. But it is a natural consequence of some versions of inflation, particularly the ones where inflation is eternal. If inflation happened once, it is probably happening somewhere else right now, in some region of space far beyond our horizon. And if it is happening there, it could spawn new universes, new bubbles, new Big Bangs. Each bubble would be causally disconnected from the others, separated by regions of space that are still inflating. We could never see them, never communicate with them, never test their existence directly. But they would be there, just as real as our own universe, just as full of galaxies and stars and possibly life. This is where quantum mechanics and cosmology converge. Quantum fluctuations do not just seed structure within a universe, they might create universes. The same process that gave us galaxies could, in principle, give rise to entirely new spacetimes, each one a separate bubble with its own beginning, its own history, its own eventual fate. The Big Bang would not be the origin of everything. It would be the origin of us, our local patch, our corner of a much larger and possibly infinite landscape. And that brings us to the edge of what physics can currently address. Beyond this point, we are in the realm of speculation, of models that make sense mathematically but have no clear way to be tested. The quantum origin of the universe is compelling. It fits the data. It makes predictions that have been confirmed, but it does not close the loop. It does not answer the ultimate question of why there is something rather than nothing. It just changes the question slightly from why is there a universe to why are there quantum fields and why do they obey the laws they obey. Some physicists think that is as far as we can go, that the laws of physics are simply given and cannot be derived from anything deeper. Others think there is more to discover, that the laws themselves might emerge from an even more fundamental structure, something we have not thought of yet. The search continues, the questions pile up, and the universe, indifferent to our puzzlement, keeps expanding, keeps evolving, keeps doing what it has always done since the first quantum fluctuation rippled through the void and set everything in motion. Those fluctuations happened, that much is certain. Whether they were the first event or merely one step in a longer chain, whether they represent the true beginning or just a transition from some prior state, those questions remain open. And the search for answers is pushing cosmology into strange new territory, into ideas that sound more like philosophy or science fiction than science, but which might turn out to be the next great leap in our understanding of where we came from and what came before. Those fluctuations happened, that much is certain. Whether they were the first event or merely one step in a longer chain, whether they represent the true beginning or just a transition from some prior state, those questions remain open. And the search for answers is pushing cosmology into strange new territory, into ideas that sound more like philosophy or science fiction than science, but which might turn out to be the next great leap in our understanding of where we came from and what came before. Because there is a possibility, a real one grounded in mathematics and physics, that the Big Bang was not the beginning. That before the expansion, before inflation, before the quantum foam and the Planck epoch, there was something else. Another universe, another phase, a cosmos that existed, aged, collapsed, and then rebounded into what we now call the Big Bang. Time, in this picture, does not start at the singularity. It stretches back indefinitely, through cycles of birth and death, expansion and contraction, an eternal rhythm with no first beat and no final note. The universe, in this view, is not a story with a beginning. It is a song that has been playing forever. This is the idea of a pre-Big Bang universe, and it comes in several flavours, each one attempting to solve the same basic problem. The problem is the singularity. General relativity predicts that if you run the expansion of the universe backward, you hit a point of infinite density and temperature where the equations break down and physics stops making sense. That singularity is a wall. You cannot see past it using the tools of classical physics, but what if the singularity is not real? What if it is an artifact of our incomplete understanding, a placeholder for something more subtle that happens when the universe reaches extreme conditions? If you could replace the singularity with some other kind of transition, a bounce or a phase change or a moment of maximum compression that does not quite reach infinity, then you could extend the history of the universe backward past the Big Bang. You could ask what came before and the question would have an answer. This is not idle speculation. There are specific mathematically detailed models that propose exactly this scenario. They go by different names: bouncing cosmology, cyclic universe, ekpyrotic universe, pre-Big Bang string cosmology. The details differ, but the core idea is the same. The Big Bang was not the origin of everything. It was a transition, a rebound, a collision, a phase flip, something that marked the end of a previous state and the beginning of ours, And if that is true, then time does not have a starting point. It extends backward, possibly forever, through an infinite series of universes that came before ours, each one living, dying, and giving birth to the next. Let's start with the simplest version of this idea, the bouncing cosmology. The concept is straightforward. Imagine the universe is currently expanding, galaxies are moving apart, space is stretching. Now imagine that at some point in the future, the expansion slows, stops, and reverses. Gravity pulls everything back together. The universe contracts, galaxies collide, space shrinks. Matter and energy get compressed into a smaller and smaller volume. In the standard Big Bang model, this contraction would end in a singularity, a big crunch, the mirror image of the Big Bang, where everything collapses into a point of infinite density and the universe ends. But in a bouncing cosmology, something different happens. Before the universe reaches the singularity, some new physics kicks in. Quantum effects, or pressure from exotic matter, or forces from extra dimensions, something intervenes and halts the collapse. The universe reaches a minimum size, bounces, and begins expanding again. The big crunch becomes a big bounce. And the expansion we see today is not the first expansion. It is just the latest one, following a contraction that came before. In this picture, the Big Bang was not the moment the universe began. It was the moment the universe rebounded from a previous contracting phase. Before the bounce, there was a universe that looked a lot like ours, except it was shrinking instead of growing. Stars were still shining, galaxies were still spinning, but the space between them was getting smaller, not larger. Eventually, that contraction reached a critical point, the bounce, and the universe flipped from shrinking to growing. Everything that existed before the bounce got compressed, heated, and scrambled, but it did not disappear. It passed through the bounce and emerged on the other side as the hot, dense plasma that we now call the early universe. The bounce itself is the tricky part. In classical general relativity, there is no mechanism to stop the collapse. Once the universe starts contracting, it keeps contracting all the way to the singularity. To get a bounce, you need something that general relativity does not include. You need quantum gravity, or some modification of gravity at high densities, or some new field or form of matter that can generate enough pressure to reverse the collapse. And you need this mechanism to kick in at exactly the right moment, when the universe is compressed to near singularity densities, but before it actually reaches the singularity. Too early and the universe bounces while it is still relatively large, which would leave observable signatures that we do not see. Too late and you hit the singularity anyway, and the bounce does not happen. Several proposals have been made for what could cause the bounce. One idea involves loop quantum gravity, a theory that attempts to quantize spacetime itself. In loop quantum gravity, space is not continuous. It is made of discrete chunks, tiny loops of gravitational field woven together into a network. At very high densities, when the universe gets compressed to the scale where these loops become important, the theory predicts a strong repulsive force that opposes further compression. This repulsive force, a kind of quantum pressure, could halt the collapse and trigger a bounce. The universe would reach a minimum size roughly at the Planck scale and then rebound. The singularity would be avoided entirely. It would be replaced by a smooth transition from contraction to expansion. Another idea involves modifications to general relativity at high energies. Some theories propose adding extra terms to Einstein's equations, terms that become significant only when the curvature of spacetime is extreme. These terms could generate a bounce by creating a pressure that opposes gravity. The details depend on the specific modification you choose, and there are many competing proposals, but the basic mechanism is the same. At normal densities, the modifications are negligible and general relativity works as usual. At extreme densities, the new terms take over and prevent the singularity. The universe bounces instead of collapsing. A third idea, and one of the most interesting, comes from string theory. String theory is a framework that attempts to unify all the forces of nature, including gravity, by replacing point particles with tiny vibrating strings. It requires extra dimensions beyond the 3 of space and 1 of time that we experience. Those extra dimensions are thought to be compactified, curled up into shapes so small that we cannot directly observe them. But they are still there, and their geometry affects the physics of the 4-dimensional universe we live in. In the early 1990s, Two physicists named Gabriele Veneziano and Maurizio Gasparini proposed a version of cosmology based on string theory, called pre-Big Bang cosmology. Their idea was that the universe did not start from a singularity, but emerged from a prior phase where the strings and extra dimensions were behaving differently. The key insight of pre-Big Bang string cosmology is that string theory has symmetries that general relativity does not. One of these is called duality. Duality means that two apparently different physical situations can actually be equivalent, just described in different ways. In particular, string theory has a symmetry that relates a very small, highly curved universe to a very large, weakly curved one. A universe that is contracting and heating up can be mathematically equivalent to a universe that is expanding and cooling down. The two descriptions are just different perspectives on the same underlying physics. Veneziano and Gasparini used this duality to argue that the Big Bang might not be a beginning but a transition. Before the Big Bang, the universe was in a different phase, a pre-Big Bang phase where it was cold, empty, and nearly flat. In this phase, the extra dimensions of string theory were large, or at least not yet compactified into their current tiny sizes. The universe was not static. It was evolving, but slowly, driven by the dynamics of the strings and fields that fill space in string theory. Over time, this pre-Big Bang phase became unstable. The universe began contracting and heating up, approaching a point of maximum curvature. But instead of hitting a singularity, the duality symmetry kicked in. The highly curved contracting universe flipped into a flat expanding one. The Big Bang was the moment of that flip, the transition from the pre-Big Bang phase to the post-Big Bang phase. And everything we see today, the expansion, the cooling, the formation of structure, is the aftermath of that transition. This is an elegant idea, and it has the advantage of being rooted in string theory, which is one of the most developed frameworks for quantum gravity. But it also has problems. For one thing, string theory is not a single, well-defined theory. It is a landscape of theories, a vast space of possible solutions, each one corresponding to a different way of compactifying the extra dimensions and choosing the values of various parameters. Different choices lead to different predictions, and we do not know which choice, if any, describes our universe. Pre-Big Bang cosmology is one corner of that landscape, and it is not the only corner. There are other string-based cosmologies that make different predictions, and distinguishing between them is hard because most of the differences show up at energy scales we cannot access experimentally. Another problem is that the transition from the pre-Big Bang phase to the post-Big Bang phase is not smooth in all versions of the model. In some versions, the transition involves a singularity or near singularity, which defeats the purpose of avoiding the singularity in the first place. In other versions, the transition is smooth, but the details depend on assumptions about the behavior of the string fields and the geometry of the extra dimensions, and those assumptions are not always well justified. The model works mathematically, but whether it describes physical reality is still an open question. Despite these challenges, pre-Big Bang cosmology opened the door to a whole new way of thinking about the origin of the universe. It showed that the Big Bang does not have to be the beginning. It can be a transition, a phase change, a moment in a longer history. And that idea has been picked up and refined by other researchers working on different models. One of the most well-known is the cyclic model, developed by Paul Steinhardt and Neil Turok in the early 2000s. Steinhardt, a physicist at Princeton, had been one of the early architects of inflation. He helped develop the theory in the 1980s and spent years refining it. But by the late 1990s, he had started to worry that inflation, for all its success, was not the final answer. Inflation solves many problems, but it also raises new ones. It requires fine-tuning of the inflaton potential. It predicts a multiverse, which many physicists find uncomfortable, and it does not explain what caused inflation to start in the first place. Steinhardt began looking for an alternative, and he found one in the idea of a cyclic universe. The cyclic model is a variation on the bouncing cosmology, but with a twist. Instead of a single bounce, the model proposes an infinite series of bounces. The universe expands, then contracts, then bounces and expands again, over and over, in a cycle that repeats forever. Each cycle lasts trillions of years. The current expansion phase, the one we are living in, is just one cycle in an endless series. Before our cycle, there was a previous one. Before that, another, and so on, stretching back infinitely into the past. There was no first cycle, the universe has always been cycling. The mechanism driving the cyclic model is tied to the geometry of extra dimensions and the physics of brains, objects from string theory that are like higher dimensional versions of membranes. In string theory, our entire universe might be a three-dimensional brain embedded in a higher dimensional space. There could be other brains nearby, separated from ours by a tiny distance in the extra dimensions. Steinhardt and Turok proposed that the cycles are driven by collisions between brains. At the end of each cycle, two brains, ours and a hidden one, drift toward each other through the extra dimensions. When they collide, the kinetic energy of the collision converts into matter and radiation, creating a hot, dense state that looks just like the Big Bang. The brains then bounce apart and the universe expands. Over trillions of years, the expansion slows, driven by the cosmological constant or dark energy, and the brains drift back together, setting up the next collision. This is the ekpyrotic scenario, from the Greek word ekpyrosis, meaning conflagration. The collision between brains is not a singular event. It is a controlled crash, a moment of enormous energy release that heats the universe and kicks off the expansion, but without requiring a singularity. The brains do not merge into a single point. They collide, bounce, and separate. The universe passes through the collision event and emerges on the other side, ready to expand again. One of the appealing features of the cyclic model is that it solves some of the same problems as inflation, but without needing an inflaton field. In the cyclic model, the flatness of the universe is explained by the fact that each cycle lasts so long that any initial curvature gets stretched out by the expansion, just like in inflation. The smoothness of the universe is explained by the fact that the brains, before they collide, are smooth and flat, and that smoothness gets imprinted on the universe when the collision occurs. The density fluctuations that seed galaxies are generated not by quantum fluctuations during inflation, but by quantum fluctuations on the brains before the collision. The math works out, and the predictions are similar to those of inflation, which means the cyclic model is consistent with the observations, but the cyclic model also has its critics. One concern is the question of entropy. Entropy is a measure of disorder, and it always increases over time in a closed system. That is the second law of thermodynamics, one of the most robust principles in physics. In a cyclic universe, entropy would accumulate from cycle to cycle. Each cycle would start with the entropy left over from the previous cycle, plus whatever new entropy is generated during the cycle. Over an infinite number of cycles, the total entropy should become infinite, and the universe should end up in a state of maximum disorder, a heat death, where nothing interesting can happen. But we do not observe that. The universe is full of structure, stars, galaxies, complexity. So how does the cyclic model avoid the entropy problem? Steinhardt and Turok argue that entropy can be diluted during each cycle. The expansion phase lasts trillions of years, during which the universe grows to an enormous size. Any entropy that existed at the beginning of the cycle gets spread out over that vast volume, lowering the entropy density. By the time the next collision occurs, the entropy density is low enough that the new cycle can start with a clean slate, or close to 1. The details are complicated, and not everyone is convinced, but the model does provide a mechanism for resetting the entropy. Whether that mechanism works in practice is still debated. Another concern is observational. If the universe is cyclic, there should be signatures of the previous cycle imprinted on the cosmic microwave background, or the distribution of galaxies. So far, no such signatures have been found. The CMB matches the predictions of inflation almost perfectly, and while the cyclic model can also explain the CMB, it does so in a way that is less natural, requiring more assumptions and fine-tuning. The cyclic model is not ruled out, but it is not the leading explanation either. It remains an alternative, a possibility that is taken seriously by some researchers, but not widely accepted. One of the most provocative aspects of the cyclic model, and of bouncing cosmologies in general, is what they imply about time. In the standard Big Bang model, time has a beginning. The singularity is not just the earliest moment in the universe's history. It is the moment when time itself started. Before the singularity, there is no before. The question of what happened earlier does not make sense, but in a bouncing or cyclic model, time extends indefinitely into the past. There was always a before. No matter how far back you go, there's another cycle, another bounce, another phase. The universe does not have a first moment. It has always existed in some form, undergoing an eternal process of expansion and contraction, or collision and separation, or some other repeating pattern. This is philosophically unsettling for some people. It removes the need for a creation event, a moment when the universe came into being. It replaces the beginning with an infinite regress, a chain of events that stretches back forever with no starting point. Some find this more satisfying than the idea of a singular beginning because it avoids the question of what caused the first cause. If there is no first cause, no need to explain where the universe came from, because it has always been here. Others find it less satisfying because it does not really answer the question. It just pushes it off to infinity. Why is there an eternal cycle? Why does the universe keep bouncing? What sustains the process? These are still open questions, and the cyclic model does not provide definitive answers. The idea of extra dimensions plays a crucial role in many of these pre-Big Bang scenarios. Extra dimensions are a prediction of string theory, and they are not just a mathematical curiosity. They could have real physical effects, especially in the early universe when the energy scales were high enough that the extra dimensions might have been larger or behaving differently than they are today. In the cyclic model, the collision between branes happens in the extra dimensions. The distance between the branes, the speed at which they approach each other, the energy released when they collide, all of this depends on the geometry and dynamics of those extra dimensions. In some models, the extra dimensions are not just passive bystanders, they actively participate in the evolution of the universe. There are scenarios where the extra dimensions expand and contract along with the three familiar dimensions of space, creating a more complex pattern of cosmic evolution. There are other scenarios where the extra dimensions are compactified, rolled up into tiny shapes, and the way they are compactified determines the properties of the particles and forces we observe in the four-dimensional universe. Changing the compactification can change the laws of physics, which raises the possibility that different cycles in a cyclic universe could have different laws. One cycle might have a different strength for electromagnetism, or a different number of particle types, or even a different number of large dimensions. The universe in this view is not just cycling in time. It is cycling through different configurations of physical law. This is speculation, and it is far from being testable, but it is grounded in the mathematics of string theory. The landscape of string theory, as it is called, is the space of all possible ways to compactify the extra dimensions and choose the parameters of the theory. That landscape is vast, containing something like 10 to the 500 different solutions, each one corresponding to a different possible universe with different laws of physics. If the universe is cycling, and if each cycle can explore a different part of the landscape, then the laws of physics we observe in our cycle are just one set among many. Other cycles could be radically different. The challenge for all of these pre-Big Bang models is connecting them to observations. The early universe is hot, dense, and opaque, which makes it hard to see through. The cosmic microwave background is the oldest light we can observe, and it comes from a time when the universe was already 380,000 years old. Everything that happened before that, including the Big Bang itself, is hidden behind a wall of plasma. To test pre-Big Bang models, we need to find indirect signatures, subtle imprints left on the CMB, or the distribution of galaxies or the properties of gravitational waves. Gravitational waves are particularly promising. If the Big Bang was a bounce or a collision, it should have generated gravitational waves, ripples in space-time that propagate outward from the event. Those waves would still be travelling through the universe today, stretched by the expansion into long wavelength signals that might be detectable by future gravitational wave observatories. The pattern of those waves, their amplitude and frequency spectrum would encode information about what happened at the bounce. Different models predict different patterns, so detecting the waves could, in principle, distinguish between competing theories. Another possible signature is in the spectrum of density fluctuations. Inflation predicts a nearly scale-invariant spectrum, meaning that fluctuations have roughly the same amplitude at all scales. Bouncing and cyclic models can also produce a nearly scale-invariant spectrum, but with subtle differences. The spectral index, the parameter that describes how the amplitude changes with scale, is slightly different in different models. Current observations of the CMB have measured the spectral index to high precision, and the results favour inflation, but they do not rule out all versions of bouncing cosmology. Future observations with better precision and at different scales might be able to make a clearer distinction. There is also the question of non-Gaussianity, the departure of the fluctuations from a perfect random distribution. Inflation predicts that the fluctuations should be very nearly Gaussian, with only tiny deviations. Bouncing models can predict larger deviations depending on the details of how the fluctuations are generated. If future observations detect significant non-Gaussianity, it could be evidence against inflation and in favour of an alternative like a bounce. So far, the data shows that the fluctuations are very close to Gaussian, which is consistent with inflation, but the search continues. One of the criticisms of pre-Big Bang models is that they are not as well developed as inflation. Inflation has been studied intensively for more than 40 years. There are hundreds of papers refining the theory, calculating its predictions, comparing it to observations. The framework is mature, the predictions are precise, and the agreement with data is excellent. Bouncing and cyclic models, by contrast, are younger and less refined. They have been proposed, and the basic mechanisms have been worked out, but many of the details are still being debated. There are multiple versions of each model, and they make different predictions, and it is not always clear which version is the most natural or the most consistent with string theory, or loop quantum gravity, or whatever underlying framework you are using. This does not mean the models are wrong, it just means they are still being developed. Science progresses by proposing ideas, testing them, refining them, and sometimes discarding them when better ideas come along. Pre-Big Bang cosmology is in the proposal and refinement stage. It has not yet reached the level of observational confirmation that inflation has, but that does not mean it never will. If future observations find signatures that inflation cannot explain, bouncing or cyclic models might move to the forefront. Science is full of examples where the underdog theory eventually won out because the data demanded it. For now, the standard picture remains the Big Bang followed by inflation. That model works. It explains the data. It makes predictions that have been confirmed. But it is not the only game in town, and the alternatives are worth taking seriously. The possibility that the Big Bang was not the beginning, that there was a universe before ours, that time extends indefinitely into the past, these are not idle fantasies. They are serious scientific proposals, grounded in the mathematics of string theory and quantum gravity, and motivated by the desire to avoid the singularity and the conceptual problems it creates. The implications of these models are profound. If the universe is cyclic, then everything that exists now has existed before in some form in previous cycles. The matter in your body, the atoms that make up the Earth, the stars in the sky, all of it has been through countless cycles of expansion, contraction, bounce, and re-expansion. You're not living in the first universe, you're living in the latest iteration of a process that has been running forever. And when this universe ends, trillions of years from now, it will not be the final end. It will bounce, or collide, or transition into a new phase, and the cycle will begin again. The universe is eternal, not in the sense of lasting forever into the future, but in the sense of having no beginning and no end. It just is, and it has always been. If the universe bounced from a prior contracting phase, then the singularity is an illusion. It is not a real event that happened. It is a mathematical artifact, a place where our equations break down because we're using the wrong equations. Replace general relativity with a theory that includes quantum gravity, and the singularity disappears. It gets replaced by a smooth transition, a moment of maximum density that is high but not infinite, a bounce that connects the past to the present without any discontinuity. The universe does not begin at the Big Bang. It passes through the Big Bang, emerging from a prior state into the expanding phase we observe today. These ideas challenge our intuitions about time and causation. We are used to thinking of time as a line with a starting point. We are used to thinking of the universe as something that was created, that came into being at a specific moment. Pre-Big Bang cosmology asks us to let go of those intuitions and accept a different picture. One where time is infinite, where the universe has always existed, where the Big Bang is not the origin, but just one event in an endless series. Whether that picture is correct is still unknown. The evidence is not yet strong enough to decide. Inflation remains the leading theory, but the alternatives are gaining traction, and the debate is far from settled. What is clear is that the question of what came before the Big Bang is no longer considered unanswerable. It is a legitimate scientific question, and people are working on it, building models, making predictions, designing experiments. The singularity is not the end of the road. It is a challenge, a puzzle, a barrier that might be overcome with the right tools and the right ideas. And as researchers push deeper into the mathematics of string theory, loop quantum gravity, and other frameworks for quantum cosmology, they are uncovering a landscape of possibilities that is richer and stranger than anyone expected. The universe might be cyclic. It might be bouncing. It might have emerged from a collision between brains in a higher dimensional space. Or it might be something else entirely, something we have not thought of yet, some mechanism or process that we will only understand when we finally have a complete theory of quantum gravity. For now, the search continues. The equations are being written, the models are being tested, the data is being analysed. And slowly, piece by piece, the picture is coming into focus. The Big Bang happened, that much is certain. But whether it was the beginning or just a transition, whether time started there or stretches back infinitely, whether our universe is the first or the latest in an eternal series, those questions are still open, and the answers, when they come, will reshape our understanding of everything. They will tell us not just where we came from, but what kind of cosmos we live in. A cosmos that had a beginning, or a cosmos that has always been here. A universe that was created, or a universe that cycles endlessly through birth and death and rebirth. And if the universe is eternal, if there was no first moment, then the next question becomes unavoidable. If our Big Bang was not the only one, if there were others before and there will be others after, how many are there? How many universes exist, hidden beyond the edge of what we can see, each one born from its own Big Bang, each one expanding and evolving and perhaps collapsing, each one a separate bubble in a vast cosmic foam that might stretch on forever? And if the universe is eternal, if there was no first moment, then the next question becomes unavoidable. If our Big Bang was not the only one, if there were others before and there will be others after, how many are there? How many universes exist hidden beyond the edge of what we can see, each one born from its own Big Bang, each one expanding and evolving and perhaps collapsing, each one a separate bubble in a vast cosmic foam that might stretch on forever? This is where cosmology stops being about our universe and starts being about universes. Plural, not just one, not even a handful, possibly an infinite number of them. The multiverse. The idea that our cosmos, everything we can see with our telescopes, every galaxy scattered across 13.8 billion light-years of observable space, all of it is just one patch in a much larger reality. One bubble in a foam, one island in an infinite ocean. And out there, far beyond the horizon of what we can ever observe, there are other universes. Some of them might look a lot like ours. Same laws of physics, same constants, just different arrangements of matter. Others might be radically different. Different forces, different particles, different rules. Some might be teeming with life. Others might be sterile, unable to form even a single star. And we would never know. We could never visit them, never communicate with them, never confirm their existence through direct observation. The multiverse is one of the most controversial ideas in modern physics. Critics call it philosophy masquerading as science. They argue that if you cannot test something, if you cannot make predictions that can be checked by experiment, then it is not science, it is speculation. Proponents argue that the multiverse is not something they are inventing for fun. It is a prediction that falls naturally out of theories we already take seriously. Inflation, string theory, quantum mechanics, all of them point toward the existence of multiple universes. Dismissing the multiverse because it is hard to test, they say, is like dismissing atoms in the 19th century because you could not see them. The evidence is indirect, but it is still evidence. The debate is fierce, and it is not going to be resolved anytime soon. But whether you believe in the multiverse or not, the idea itself is worth understanding. Because if it is real, it changes everything. It changes what it means to ask why the universe is the way it is. It changes the significance of the Big Bang. It changes what we mean when we talk about the origin of reality. And it forces us to confront a question that most of us would rather avoid. Are we special, or are we just lucky? The multiverse comes in several flavors. Physicists have sorted them into levels, a hierarchy of increasingly strange and increasingly speculative possibilities. The simplest version is called the Level 1 multiverse, and it is almost uncontroversial. The idea is straightforward. The observable universe, the region of space we can see, is finite. It is bounded by the distance that light has had time to travel since the Big Bang. Look far enough in any direction and you hit a horizon, a limit beyond which light has not had time to reach us. That does not mean space stops there. Space could be infinite. In fact, most cosmological models assume it is. If space is infinite, then there are regions far beyond our horizon, regions we can never see because light from them has not had time to arrive and never will, because the expansion of space is carrying them away faster than light can close the gap. Now here is where it gets interesting. If space is infinite and if the laws of physics are the same everywhere, then the same kinds of structures we see in our observable universe should exist out there too. Galaxies, stars, planets, all of it. The initial conditions after the Big Bang were slightly different from place to place, driven by quantum fluctuations during inflation, and those differences seeded the structure we see. But quantum fluctuations are random. Over an infinite space, every possible configuration of matter will eventually repeat. Somewhere out there, far beyond the edge of what we can see, there is a region of space that looks exactly like our observable universe. Same galaxies in the same position, same stars, same planets, same history. And on one of those planets, there is a person who looks exactly like you, listening to a video exactly like this one, wondering the same things you are wondering right now. This is not science fiction. This is a consequence of taking infinity seriously. If space is infinite, and if the number of possible configurations of matter is finite, which it is because quantum mechanics allows only a finite number of distinguishable states within a given volume, then repetition is inevitable. The math works out. Within a sphere of about 10 to the 118 meters from here, there should be an exact duplicate of our observable universe. That is an unimaginably large distance, far larger than the observable universe itself, but it is finite, and if space is infinite, that distance exists somewhere. So your doppelganger is out there, many of them actually, an infinite number of them, each living in a region of space that is identical to ours in every detail. This version of the multiverse is the least controversial because it does not require any new physics. It just requires space to be infinite, which many cosmological models already predict. The observable universe is finite, but the universe itself might not be, and if it is not, then the level 1 multiverse is real. We just cannot ever confirm it because those other regions are forever beyond our reach. The expansion of space ensures that the distance between us and them is growing faster than light, so no signal from there can ever get here, and no signal from here can ever get there. We are causally disconnected, two bubbles in an infinite expanse, each one oblivious to the other. The level 2 multiverse is stranger and more controversial. This is the one that comes from eternal inflation. We talked about inflation earlier, the brief period of exponential expansion that stretched a tiny patch of space into something the size of a galaxy or larger. Inflation solves several problems in cosmology, and it is supported by a lot of evidence. But the models that describe inflation have a peculiar feature. Once inflation starts, it is hard to stop. Everywhere. Here is how it works. Inflation is driven by the inflaton field, a hypothetical field that fills space and has a lot of potential energy. When the field is sitting near the top of its potential, in a region where the potential is nearly flat, it generates a negative pressure that drives exponential expansion. Eventually the field rolls down its potential and settles into a lower energy state, and inflation ends. The field decays into particles, and the universe transitions into the more familiar hot Big Bang phase. That is what happened in our region of space. The inflaton field decayed, inflation stopped, and we got a universe full of matter and radiation. But in other regions, the field might not have decayed yet. Inflation might still be going on. The reason is quantum mechanics. The inflaton field, like any quantum field, is subject to fluctuations. In some regions, those fluctuations push the field down the potential, causing it to decay and inflation to end. In other regions, the fluctuations push the field back up the potential, keeping it in the inflating state. And because space is expanding exponentially in the regions where inflation is still happening, those regions grow faster than the regions where inflation has ended. The volume of space that is still inflating increases over time, even though pockets of non-inflating space are constantly being carved out of it. The result is a process called eternal inflation. Inflation never completely stops. It keeps going forever in some parts of space while ending in others. Each pocket where inflation ends becomes a bubble universe, a region with its own Big Bang, its own initial conditions, its own history. Our universe is one such bubble, and out there, scattered through the eternally inflating background, there are other bubbles, lots of them. Possibly an infinite number of them, each one a separate universe with its own properties. This is the Level 2 multiverse, and it is more interesting than the Level 1 version, because the bubbles do not all have to be the same. The Level 1 multiverse just has different regions of the same space with different arrangements of matter. The Level 2 multiverse has different bubbles with potentially different laws of physics. The reason comes from string theory and the landscape of possible vacua. String theory, if you're not familiar with it, is a framework that attempts to unify all the forces of nature by replacing point particles with tiny vibrating strings. It requires extra dimensions beyond the 3 of space and 1 of time that we experience, and those extra dimensions need to be compactified, curled up into shapes too small to see. The way you compactify the extra dimensions determines the properties of the 4-dimensional universe you observe. Different compactifications give you different masses for particles, different strengths for forces, different numbers of particle types. String theory does not predict a single unique universe. It predicts a landscape of possible universes, a vast space of solutions, each one corresponding to a different way of compactifying the extra dimensions. The landscape is huge. Estimates suggest there are something like 10 to the 500 different possible vacua in string theory, each one a different way of setting up the extra dimensions and choosing the parameters of the theory. That is a number so large it defies comprehension. For comparison, the number of atoms in the observable universe is about 10 to the 80. 10 to the 500 is 10 to the 80 raised to the 6th power, and then some. It is not just a lot, it is a stupidly large amount. Now combine eternal inflation with the string landscape. As inflation carves out bubble universes, different bubbles can settle into different vacua. The inflaton field, as it decays, does not necessarily end up in the same state in every bubble. Quantum fluctuations during the decay process can push it into different regions of the string landscape. One bubble might end up in a vacuum where the electron has a certain mass and electromagnetism has a certain strength. Another bubble might end up in a vacuum where those values are different. The laws of physics, at least the low-energy laws that we observe, can vary from bubble to bubble. This is a radical idea. It means the constants we measure, the strength of gravity, the mass of the electron, the speed of light, all of it might not be fundamental. They might just be environmental parameters, specific to our bubble, the way the temperature and pressure at sea level on Earth are specific to this planet. Other bubbles would have different constants. Some of them might be similar to ours, others might be wildly different. And we would have no way to predict which bubble we would find ourselves in because the process is fundamentally random, governed by quantum fluctuations. If the Level 2 multiverse is real, then the question of why the constants have the values they do is no longer a deep mystery. They have the values they do because we are in a bubble, where those values allow for the existence of observers. In bubbles with different constants, different things happen. Some bubbles might not form stars, others might not form atoms. The chemistry needed for life might be impossible. Those bubbles are just as real as ours, but they are empty. No one is there to ask why the constants are what they are because no one can exist there. We are in a bubble where the constants are right for life, not because the constants were chosen or fine-tuned, but because we could not be anywhere else. This is called the anthropic principle, and it is one of the most contentious ideas in physics. The anthropic principle comes in different strengths. The weak version just says that we should not be surprised to find ourselves in a universe that allows for our existence. That is obvious. If the universe did not allow for life, we would not be here to wonder about it. The strong version goes further. It says that the constants have the values they do because those values are necessary for observers to exist, and the multiverse provides a mechanism for exploring different values. Most bubbles are sterile, a few are not. We are in one of the non-sterile ones. That is not a deep fact about the universe, it is a selection effect. Critics of the anthropic principle hate this argument. They see it as giving up. Instead of looking for a deeper explanation for why the constants are what they are, the anthropic principle just says they are what they are because otherwise we would not be here. It replaces prediction with post-diction. It turns physics into a kind of cosmic lottery where we just got lucky. and it raises the question of whether the multiverse explanation is any better than just saying God did it, or it is just that way. You're replacing one mystery with another, and the new mystery, the multiverse, is even harder to test than the old one. Proponents argue that the anthropic principle is not giving up. It is recognizing that some questions might not have the kind of answers we were expecting. The constants might not be derivable from a deeper theory. They might just be random variables that take different values in different bubbles, and the only constraint on their values in our bubble is that they have to allow for life. That is a scientific prediction. You can calculate which range of constants allows for stars, planets, chemistry, life, and you can compare that to the values we observe. If the observed values fall within the allowed range, the anthropic explanation works. If they fall far outside it, the explanation fails. The most famous example of this is the cosmological constant, the parameter that describes the energy density of the vacuum. In quantum field theory, the vacuum should have a huge energy density, something like 120 orders of magnitude larger than what we observe. This is called the cosmological constant problem, and it is one of the worst predictions in the history of physics. The observed value of the cosmological constant is tiny, almost zero, but not quite. If it were much larger, the universe would have expanded so fast that galaxies could never form. If it were negative, the universe would have collapsed long ago. The range of values that allows for the existence of structure is narrow, and the observed value falls right in the middle of that range. In the 1980s, Steven Weinberg, a Nobel Prize-winning physicist, pointed out that if the multiverse is real, and if the cosmological constant varies from bubble to bubble, then the anthropic principle predicts that we should find ourselves in a bubble where the constant is small enough to allow galaxies to form. He calculated the range of values that would be compatible with observers, and the observed value fit. At the time, this was considered a curiosity. Most physicists were hoping for a deeper explanation, some symmetry or principle that would explain why the cosmological constant is small. But no such explanation has been found, and the anthropic prediction remains one of the few that has worked. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating, driven by something that looks like a cosmological constant. The measured value matched Weinberg's anthropic prediction. This was a surprise. It was also a vindication for those who believed in the multiverse. The cosmological constant is not zero, and it is not large. It is small, just barely large enough to be detectable, and just small enough to allow for the formation of galaxies. That is exactly what the anthropic principle predicts if the multiverse is real. But not everyone is convinced. The problem is that the anthropic principle, combined with the multiverse, is so flexible that it can explain almost anything. You can always argue that we observe what we observe because other values would not allow for observers. That makes it hard to falsify. If a theory explains everything, it might explain nothing. It becomes a just-so story, a way of making sense of the data after the fact without making any risky predictions. Critics argue that this is not science. Science requires falsifiable predictions. The multiverse, they say, is unfalsifiable because we can never observe the other universes. It is metaphysics, not physics. Proponents counter that the multiverse does make predictions. It predicts, for example, that the constants we observe should be typical for a universe that allows observers, not finely tuned to some optimal value. If the constants were perfectly optimized for life, that would be evidence against the multiverse and in favor of some kind of design or deeper principle. But if they are just barely good enough, sitting near the edge of the allowed range, that is what you expect from a random selection process. The cosmological constant is a good example. It is small, but not optimally small. It is just small enough. That fits the multiverse picture. There is also the question of testability. While we cannot directly observe other universes in the Level 2 multiverse, we might be able to find indirect evidence. If two bubbles collide, the collision could leave a signature in the cosmic microwave background, a circular pattern or temperature anomaly that shows where our bubble was hit by another one. Several groups have searched for such signatures in the CMB data. So far, nothing conclusive has been found, but the search continues. A collision would be a smoking gun, direct evidence that other bubbles exist. The absence of a collision does not prove anything. Our bubble could be isolated, or the collisions could be rare enough that we have not seen one yet. Another possible test comes from the statistical distribution of constants across the multiverse. If eternal inflation is correct, And if the string landscape is real, then there should be a probability distribution over the different vacua. Some vacua should be more common than others, depending on the dynamics of the inflaton field and the structure of the landscape. If we could calculate the distribution, we could make predictions about what values of the constants are most likely to be observed by a randomly selected observer. Those predictions could then be compared to the values we actually measure. If the predictions match, it is evidence for the multiverse. If they do not, it is evidence against. The trouble is that calculating the probability distribution is fiendishly difficult. This is called the measure problem in eternal inflation, and it is one of the biggest unsolved issues in the field. The problem is that in an eternally inflating multiverse, there are infinitely many bubbles and infinitely many observers. To calculate probabilities, you need to compare the number of observers who see one set of constants to the number who see another set. But when both numbers are infinite, the comparison depends on how you count. Different ways of counting give different answers, and there is no universally agreed upon prescription for which counting method is correct. Until the measure problem is solved, the multiverse cannot make sharp predictions. So the level 2 multiverse is fascinating, but it is also frustrating. It offers a potential explanation for some of the biggest puzzles in cosmology, like the fine-tuning of the constants. But it does so in a way that is hard to test and that raises new puzzles of its own, like the measure problem. It is not clear whether the multiverse is a step forward or a step sideways, replacing one set of mysteries with another. Then there is the level 3 multiverse, which is even stranger. This one comes from quantum mechanics, specifically from the many worlds interpretation. We talked about quantum mechanics earlier, how particles exist in superpositions of multiple states until they are measured, at which point the superposition collapses and one definite outcome is realized. The many worlds interpretation says that the collapse does not actually happen. Instead, every possible outcome is realized, but in different branches of the wave function. When you measure a particle and find it in a particular state, the universe splits. In one branch, the particle is in that state. In another branch, it is in a different state. Both branches are real. Both continue to exist. They just do not interact with each other. In the many worlds picture, the universe is constantly branching. Every quantum measurement, every random event, every moment where the laws of quantum mechanics allow multiple outcomes, the universe splits into multiple copies, one for each possible outcome. The number of branches grows exponentially. After just a few seconds, there are an unimaginable number of parallel worlds, each one slightly different from the others. In some branches, you made different choices. In others, different particles decayed at different times, leading to different histories. The branching is so pervasive that every possible history, consistent with the laws of quantum mechanics, is realized somewhere in the multiverse of branches. The level 3 multiverse is not the same as the level 2 multiverse. The level 2 multiverse involves different regions of space, different bubbles carved out by eternal inflation. The level 3 multiverse involves different branches of the quantum wave function, different versions of the same space. They are parallel in a different sense. They occupy the same physical location, but they are separated by decoherence, the process that prevents quantum branches from interfering with each other. You cannot visit another branch. You cannot send a signal to it. It is as inaccessible as another bubble universe in the level 2 multiverse. Some physicists argue that the level 3 multiverse is actually less extravagant than the level 2 version. In the level 2 multiverse, you are postulating an enormous number of physically distinct regions of space, each one with its own matter and energy. In the level 3 multiverse, you're not adding any new matter or energy. You're just taking the quantum wave function seriously and following it to its logical conclusion. All the branches are described by a single wave function, a single mathematical object. The multiverse of branches is, in some sense, simpler than a single collapsing wave function, because it does not require you to postulate an additional mechanism for collapse. The wave function just evolves according to the Schrödinger equation, and the branching happens automatically. Critics of many worlds argue that the interpretation is extravagant in a different way. It postulates an infinite number of unobservable worlds. Every time a particle decays, the universe splits. Every time a photon hits your eye, the universe splits. The branching is relentless, and the number of branches is staggering. Most physicists are uncomfortable with the idea that every possible outcome is realized. It feels like overkill. But the many worlds interpretation has defenders, and their number has been growing. The interpretation makes the same predictions as other interpretations of quantum mechanics, so it is empirically equivalent. You cannot test it against the standard collapse interpretation by doing experiments. The choice between them is a matter of philosophy, of which framework you find more conceptually satisfying. There is also a level 4 multiverse, proposed by the cosmologist Max Tegmark. This is the most speculative version, and it is based on the idea that mathematical structures are not just descriptions of reality, but are reality. Every logically consistent mathematical structure corresponds to a real universe. Our universe is one such structure. Other mathematical structures, with different rules and different entities, are other universes. This is called the mathematical universe hypothesis, and it is deeply controversial. Most physicists do not take it seriously, but it is worth mentioning because it represents the extreme end of multiverse thinking. If the level 4 multiverse is real, then not only are there many universes with different constants, there are universes with entirely different kinds of mathematics, different logics, different structures. Anything that can be described mathematically exists. For the purposes of this discussion, we will focus on the level 2 and level 3 multiverses, which are the versions most closely tied to well-established physics. The level 2 multiverse comes from inflation and string theory. The level 3 multiverse comes from quantum mechanics. Both are grounded in frameworks that have been extensively tested and are taken seriously by physicists. Neither is proven, but both are plausible. The implications of the multiverse are profound. If it is real, then our universe is not special. The Big Bang was not a unique event. It was just one bubble nucleating out of an eternally inflating background, or one branch splitting off from the quantum wave function. The constants we observe, the laws we measure, the history we have lived, all of it is specific to our patch of the multiverse. Other patches have different constants, different laws, different histories. Some of them might be similar enough to ours that life could exist there. Others might be so different that nothing resembling life is possible. This changes the meaning of the question, why is the universe the way it is? In a single universe, that question demands a deep answer. There must be some reason, some principle, some law that fixes the constants to the values we observe. But in a multiverse, the question becomes less urgent. The constants are what they are in our bubble, because they have to be within a certain range for us to exist. That is not a deep fact about the universe. It is a selection effect. We are in this bubble because it is one of the bubbles that allows for observers. Some people find this depressing. It removes the sense that the universe was made for us, that there is something special about the way things are. It replaces purpose with accident. We're not living in the one true universe, the only one that could have existed. We are living in one bubble among an infinite foam, and the only reason we're here is that this particular bubble happened to have the right properties. Other bubbles exist, but they are empty. We are not special. We are just lucky. Others find the multiverse idea exhilarating. It means the cosmos is far larger and richer than we ever imagined. Reality is not confined to what we can see. It extends far beyond, encompassing an infinite variety of possibilities. Some of those possibilities might be home to other forms of life, other intelligences, other civilizations asking the same questions we're asking. We will never meet them. They are too far away, separated from us by vast expanses of inflating space or by the decoherence that isolates quantum branches. But they are there. The multiverse is not empty. It is full of worlds. The philosophical shift is significant. For most of human history, we have thought of the universe as a single, unified whole. One cosmos, governed by one set of laws, with one history stretching from the beginning to the end. The multiverse fractures that picture. It replaces the singular with the plural. There is no longer one universe. There are many, possibly infinitely many, each one a separate domain with its own story. Our story is just one thread in a much larger tapestry. The challenge, as always, is evidence. How do you test the multiverse? If other universes are causally disconnected from ours, if we can never observe them or interact with them, then how can we ever know they are real? This is the central criticism, and it is a serious one. Science is built on observation and experiment. Theories that make no testable predictions are not science, no matter how elegant or mathematically compelling they are. If the multiverse cannot be tested, then it belongs in the realm of philosophy or metaphysics, not physics. But the situation is not as hopeless as it sounds. While we cannot directly observe other universes, we can test the theories that predict them. Inflation is testable. We have confirmed many of its predictions, like the flatness of the universe and the nearly scale-invariant spectrum of density fluctuations. If future observations find evidence that contradicts inflation, the Level 2 multiverse would be in trouble. String theory is harder to test because it makes predictions at energy scales far beyond what we can access with current accelerators. But it is not completely untestable. The theory makes some predictions about the low energy physics we observe, and it could be constrained or ruled out by future experiments. The many worlds interpretation of quantum mechanics is even trickier because it makes exactly the same predictions as other interpretations. You cannot do an experiment that distinguishes many worlds from collapse models. The choice between them is a matter of interpretation, of how you think about the wave function and what it represents. Some physicists argue that this means the question is not a scientific one. Others argue that simplicity and conceptual clarity are legitimate criteria for choosing between theories, and that many worlds is simpler because it does not require an additional collapse mechanism. The multiverse also makes some specific predictions that can, in principle, be tested. If bubble collisions happen, they should leave marks in the cosmic microwave background. If the anthropic principle is correct, the constants we observe should be typical for observers, not optimally tuned. These predictions are vague, and testing them is difficult, but they are not impossible. The multiverse is not completely beyond the reach of science. It is just at the edge, in that uncomfortable zone where theory and observation barely touch. There is also the question of whether the multiverse is the right explanation for the fine-tuning of the constants. Some physicists argue that fine-tuning is not a problem that needs solving. The constants are what they are, and asking why they have those values is like asking why the sky is blue. It just is. The laws of physics determine the values, and if we knew those laws well enough, we could calculate them. The fact that we cannot calculate them yet does not mean we need to invoke a multiverse. It just means we do not have a complete theory yet. Others argue that the fine-tuning is too striking to ignore. The cosmological constant is one example. The masses of fundamental particles are another. Change some of those values by even a small amount, and the universe becomes unrecognizable. Stars do not form, atoms do not bond, life is impossible. The range of values that allows for a universe like ours is narrow, and the observed values fall right in the middle of that range. That could be a coincidence, or it could be a clue that something deeper is going on. The multiverse offers one possible explanation. There might be others. What is clear is that the multiverse is not a fringe idea. It is taken seriously by a significant fraction of the cosmology community. Papers on eternal inflation, the string landscape, and the anthropic principle appear regularly in top journals. Conferences are held. Debates are vigorous. The idea is controversial, yes, but it is mainstream controversial. It is not pseudoscience. It is an active area of research, with smart people working hard to figure out whether it is true and how to test it. And that brings us back to the fundamental question. Is the multiverse real? Are there other universes out there, beyond the edge of what we can see, each one with its own Big Bang, its own history, its own set of laws? Or is our universe the only one, a singular creation with constants that were somehow chosen or fixed by a deeper principle we have not discovered yet? The answer is not yet known. The evidence is indirect and inconclusive. The theories are incomplete. The tests are difficult and in some cases impossible. But the question is worth asking, and the search for answers is worth pursuing. Because if the multiverse is real, it changes everything. It changes what it means to ask where we came from. It changes the significance of the Big Bang. It changes our place in the cosmos. We are not at the center of everything. We are not even at the center of our own universe. We are on a small planet orbiting an average star in an average galaxy in one bubble among possibly infinite bubbles, each one a universe unto itself. That is a humbling thought. It is also an inspiring one. The reality we inhabit is far larger than we ever imagined. And somewhere out there in the vast expanse beyond our horizon, there might be other worlds, other lives, other stories playing out. We will never see them. We will never know them. But they might be there nonetheless, and that possibility alone is enough to make you stop and think about what it means to exist at all. The multiverse reframes the question of our origins from why did this universe begin into why does anything exist, and whether that anything is one cosmos or infinitely many, the puzzle remains. And solving that puzzle will require more than just thinking about bubbles and branches and alternate realities. It will require a theory that can describe the moment when everything, the laws, the constants, the fabric of space-time itself, first emerged from whatever came before. It will require a theory of quantum gravity. The multiverse reframes the question of our origins from why did this universe begin into why does anything exist, and whether that anything is one cosmos or infinitely many, the puzzle remains. And solving that puzzle will require more than just thinking about bubbles and branches and alternate realities. It will require a theory that can describe the moment when everything, the laws, the constants, the fabric of space-time itself, first emerged from whatever came before. It will require a theory of quantum gravity. Quantum gravity. 2 words. Physicists have been chasing those 2 words for the better part of a century, and they are still chasing them. Not because they are lazy, not because they are not smart enough, but because the problem is genuinely brutally hard. It might be the hardest problem in all of physics. You're trying to unify 2 theories that are both spectacularly successful, both tested to extraordinary precision, and both fundamentally incompatible with each other. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes particles and forces at the smallest scales. They work beautifully in their own domains. But when you try to bring them together, when you try to apply both at the same time in the same place, the equations break down. They produce infinities. They stop making sense. And that breakdown happens exactly where you need them most, at the very beginning of the universe, in the first tiny fraction of a second after the Big Bang, in the regime where space-time is so violently curved and so microscopically small that neither theory can function on its own. This is not a philosophical problem, this is a physics problem. Without a theory of quantum gravity, we cannot describe the Planck epoch. We cannot say what happened at the Singularity. We cannot answer the question of what came before the Big Bang, or whether before even makes sense. We are stuck at a wall, and the only way past that wall is to find a theory that unifies general relativity and quantum mechanics into a single coherent framework. That theory is quantum gravity, and we do not have it yet. We have candidates, we have proposals, we have frameworks that look promising, but none of them are complete. None of them have been experimentally confirmed, and the gap between what the theories predict and what we can actually test is in most cases absurdly large. The energy scales where quantum gravity becomes important are about 10 to the 19 billion electron volts. That is the Planck energy, and it is roughly a quadrillion times higher than anything we can produce in the Large Hadron Collider. Building an accelerator powerful enough to probe the Planck scale directly would require a machine the size of the galaxy. We are not going to build that machine. So the usual method of testing physics, smashing particles together at high energies and seeing what happens, is not an option. Quantum gravity has to be tested indirectly, through its predictions about the early universe, through subtle effects that might show up in the cosmic microwave background, or in the behavior of black holes, through mathematical consistency and conceptual clarity. It is a different kind of science, and it requires a different kind of patience. The fundamental conflict between general relativity and quantum mechanics shows up most starkly at the Planck scale. The Planck scale is not a place. It is a set of natural units derived from 3 fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. Combine them in the right way and you get a length scale, a time scale, and an energy scale. The Planck length is about 1.616 times 10 to the negative 35 meters. That is 20 orders of magnitude smaller than a proton. The Planck time is about 5.4 times 10 to the negative 44 seconds. That is the time it takes light to cross a Planck length. The Planck energy is about 10 to the 19 billion electron volts, as mentioned. These are the natural scales of quantum gravity. Below the Planck length, the concept of distance might not even make sense. Below the Planck time, the concept of duration might break down. At the Planck energy, space-time itself is expected to be in a quantum state, fluctuating and foaming and behaving in ways that our current theories cannot describe. General relativity treats space-time as a smooth, continuous fabric. You can zoom in as far as you like and it is still smooth. There is no graininess, no minimum distance, no fundamental discreteness. The theory works by describing how matter and energy curve spacetime, and how that curvature affects the motion of matter and energy. It is a classical theory, meaning it does not include quantum effects, and it works spectacularly well at large scales. It predicts the orbit of planets, the bending of light around stars, the existence of black holes, the expansion of the universe. Every test we have thrown at it, it has passed. Quantum mechanics, on the other hand, is built on discreteness and uncertainty. Particles do not have definite positions until they are measured. Energy comes in discrete chunks. The vacuum is not empty but filled with fluctuating fields. The theory describes a fundamentally probabilistic world where outcomes are determined by wave functions and probabilities, not by deterministic trajectories, and it works spectacularly well at small scales. It explains the structure of atoms, the behaviour of electrons, the properties of light, the forces between particles. Every test we have thrown at it, it has passed. The problem is that the two theories are based on incompatible assumptions. General relativity assumes space-time is a fixed, smooth background. Quantum mechanics assumes a fixed background too, but it treats matter and energy as quantum fields living in that background. When you try to make space-time itself a quantum field, when you try to quantize gravity the way you quantize electromagnetism, the whole thing falls apart. The equations produce infinities that cannot be removed by the usual tricks physicists use to deal with infinities in other quantum field theories. Gravity, it turns out, is not renormalizable. That's the technical term, and it means that the theory breaks down at high energies. You cannot make sense of quantum gravity using the standard methods of quantum field theory. This is where the two leading candidates for a theory of quantum gravity come in: string theory and loop quantum gravity. They take very different approaches, and they are based on very different philosophies. String theory starts with particles, and tries to make them into something that can naturally include gravity. Loop quantum gravity starts with space-time, and tries to quantize it directly. Both are ambitious, both are mathematically sophisticated, both have passionate advocates and vocal critics, and both are incomplete. Let's start with string theory because it is the older of the two and the one that has gotten the most attention. String theory was born in the late 1960s, not as a theory of quantum gravity but as a theory of the strong nuclear force, the force that holds quarks together inside protons and neutrons. It did not work very well for that purpose, and it was mostly abandoned. Then, in the mid-1970s, physicists realised that string theory naturally includes a particle with the right properties to be the graviton, the hypothetical quantum of the gravitational field. If you quantize gravity, you expect gravitational waves to come in discrete packets, just like light comes in packets called photons. Those packets are gravitons, and string theory predicts them automatically. That was a huge surprise. It meant string theory was not just a theory of particles, it was a theory of everything. A framework that could potentially unify all the forces of nature, including gravity. The basic idea of string theory is simple to state, though the math is anything but. Instead of thinking of fundamental particles as points, as we do in the standard model of particle physics, string theory says they are tiny vibrating loops of energy, strings. These strings are incredibly small, about the Planck length, which is why they look like points in every experiment we have ever done. But they are not points, they have extension. They vibrate, and the different modes of vibration correspond to different particles. An electron is a string vibrating one way, a quark is a string vibrating another way, a photon is a string vibrating yet another way. Every particle in the standard model, and some that are not in the standard model, is just a different note played on the same fundamental string. This is an elegant idea. It replaces the zoo of fundamental particles, dozens of them, each with its own properties and its own role, with a single object, the string. The diversity of particles is explained by the diversity of vibrations, the way a single violin string can produce different notes depending on how it is bowed. And because the string has extension, it does not suffer from the same problems that point particles do. When you try to calculate the interactions of point particles at very high energies, you get infinities because the points can get arbitrarily close together, and the forces between them can become arbitrarily strong. Strings, on the other hand, are smeared out over a small but finite region. That smearing softens the interactions and removes the infinities. String theory is, in technical terms, finite. It does not produce the uncontrollable infinities that plague other attempts to quantize gravity. But string theory comes with a cost, a big one. The theory only works in more than 4 dimensions. Depending on which version of string theory you're working with, you need either 10 or 11 dimensions of space-time. That is 9 or 10 dimensions of space plus 1 of time. We only observed 3 dimensions of space and 1 of time. So where are the extra dimensions? The answer, according to string theory, is that the extra dimensions are compactified. They are curled up into tiny shapes, so small that we cannot detect them. Imagine a garden hose. From a distance, it looks like a one-dimensional line. You can move forward or backward along the hose, and that is it. But if you zoom in close enough, you see that the hose has thickness. There is a second dimension, the circular dimension around the hose, that was not visible from far away. String theory says the same thing is happening with the extra dimensions. They are there, but they are rolled up into shapes so small on the order of the Planck length that we cannot see them. Every point in our 3-dimensional space actually has 6 or 7 extra dimensions attached to it, but those dimensions are compact and hidden. The geometry of those extra dimensions matters. The way they are compactified determines the properties of the particles and forces we observe in the 4-dimensional world. Different shapes, different compactifications give you different low-energy physics. This is both a strength and a weakness. It means string theory is incredibly flexible. It can, in principle, reproduce the standard model of particle physics by choosing the right compactification. But it also means the theory does not make a single unique prediction. There are an enormous number of possible compactifications, each one corresponding to a different vacuum, a different possible universe. This is the string landscape, which we talked about in the Multiverse chapter. The landscape is vast, with something like 10 to the 500 different vacua, each one a different way of setting up the extra dimensions, and we have no idea which one, if any, describes our universe. That is a problem. Science is supposed to make predictions. A theory that can explain anything explains nothing. If you can tweak the compactification to fit whatever data you have, then the theory is not really being tested. It is being adjusted. String theorists argue that this is not as bad as it sounds. The theory still makes general predictions, like the existence of extra dimensions, the presence of supersymmetry at high energies, the behavior of black holes. Some of those predictions might be testable, even if the specific details of the compactification are not. But the critics are not satisfied. They point out that string theory has been around for more than 40 years, and it has not made a single confirmed prediction about the real world. No experiment has found evidence of extra dimensions. No experiment has found supersymmetric particles. No experiment has found strings. The theory is mathematically beautiful, but it has no experimental support. In the mid-1990s, string theory underwent a revolution. Physicists realized that the 5 different versions of string theory that had been developed, each one seeming to describe a different world, were actually 5 different limits of a single underlying theory. That theory is called M-theory. The M stands for, well, nobody's quite sure. Membrane maybe, or mother, or mystery. M-theory is 11-dimensional, 1 dimension more than the earlier string theories, and it includes not just strings but higher dimensional objects called branes. A brane is a generalization of a membrane, a 0 brane is a point, a 1 brane is a string, a 2 brane is a membrane. A 3 brane is a 3-dimensional volume, and so on. In M-theory, our entire observable universe could be a 3 brane embedded in a higher dimensional space. We live on the brane, and we cannot move off it because the particles and forces we interact with are confined to the brane. Gravity, on the other hand, can leak into the extra dimensions, which is why it is so much weaker than the other forces. This is a provocative idea, and it has inspired a lot of research, including the cyclic cosmology we discussed earlier. But M-theory is even less developed than string theory. It exists as a set of interconnected insights, a web of dualities and symmetries that hint at a deeper structure, but there is no complete formulation. No one has written down the equations of M-theory in a way that you can solve and make predictions from. It is a framework, a roadmap, a promise of a theory, but not yet a theory in the full sense. So that is string theory. Elegant, mathematically rich, frustratingly hard to test. It might be the right answer, it might be completely wrong. We do not know yet. Loop quantum gravity takes a different approach. Instead of starting with particles and trying to incorporate gravity, it starts with gravity and tries to quantize it. Loop quantum gravity, or LQG, takes general relativity seriously as a description of spacetime and asks, What happens if you apply the rules of quantum mechanics directly to spacetime itself? The answer, according to LQG, is that spacetime is not continuous. It is made of discrete quantized chunks. Just like energy comes in discrete packets and angular momentum comes in discrete units, area and volume come in discrete units in LQG. The smallest possible area is roughly 2.6 times 10 to the negative 70 square meters, about the Planck area. The smallest possible volume is about 4 times 10 to the negative 105 cubic meters, about the Planck volume. Below those scales, the concept of area or volume does not make sense. Space is not smooth. It is granular, like a fabric woven from individual threads. The threads, in LQG, are called spin networks. A spin network is a graph, a collection of nodes connected by edges, and each edge carries a quantum number representing the geometry of a tiny piece of space. The nodes represent volumes, and the edges represent areas. The entire geometry of space is encoded in the structure of the spin network. If you want to know the distance between 2 points, you look at the spin network and calculate it from the quantum numbers on the edges. Space-time is not a continuous fabric. It is a network, a web of discrete connections, and the smooth geometry we observe at large scales emerges from the collective behavior of trillions upon trillions of these tiny quantum threads. Loop quantum gravity has a big advantage over string theory. It is explicitly background independent. That is a fancy way of saying the theory does not assume spacetime exists as a fixed stage. In most quantum field theories, you start with a background spacetime, usually flat Minkowski space, and you describe how fields and particles behave in that background. But in general relativity, spacetime is not a background. It is dynamical. It curves and bends in response to matter and energy. Loop quantum gravity respects that. It does not assume a background. It builds spacetime from the bottom up, from the quantum network. That is philosophically satisfying. It is also technically demanding. One of the main predictions of LQG is that the Big Bang singularity is resolved. In classical general relativity, the universe starts at a singularity, a point of infinite density and temperature where the equations break down. In LQG, the singularity is replaced by a bounce. As the universe contracts toward the singularity, quantum effects kick in. The density reaches a maximum somewhere around the Planck density, and then the universe bounces. It transitions from a contracting phase to an expanding phase without ever reaching infinite density. The singularity is avoided. The Big Bang is not a beginning. It is a transition, a quantum bounce from a previous contracting universe. This is a bold prediction, and it is one of the main selling points of LQG. If the singularity is resolved, then the universe has a history that extends backward past the Big Bang. Time does not start at the singularity. It keeps going through the bounce and into the previous phase. This fits naturally with the bouncing cosmologies we discussed earlier, and it provides a mechanism for the bounce that is grounded in quantum gravity, rather than just postulated. But LQG has problems too. The biggest one is that it has not yet been shown to reproduce general relativity at large scales. In the quantum regime, near the Planck scale, LQG describes a discrete granular spacetime. But at large scales, spacetime looks smooth. How does the smooth geometry of general relativity emerge from the quantum network? That is called the semi-classical limit, and it is a hard problem. You need to show that when you take a huge number of spin networks and average over them, you get the familiar smooth spacetime described by Einstein's equations. Some progress has been made, but the full semi-classical limit has not been demonstrated. Until it is, LQG is incomplete. It might describe the quantum regime beautifully, but if it does not give you back general relativity at large scales, then it is not a theory of our universe. Another problem is that LQG does not naturally include the other forces. It is a theory of quantum gravity, but it does not unify gravity with electromagnetism or the strong and weak nuclear forces. String theory, for all its problems, at least attempts to be a theory of everything, a framework that includes all the forces in a single package. LQG is more modest. It focuses on gravity, and it leaves the other forces for later. That might be the right approach. Maybe you should solve gravity first and worry about unification later. Or maybe you need to tackle everything at once. It is not clear. There are other approaches to quantum gravity besides string theory and loop quantum gravity, though these two are the most developed. There is causal dynamical triangulations, a framework that builds spacetime from tiny simplices, the higher dimensional analogues of triangles, and sums over all possible ways of gluing them together. There is asymptotic safety, a program that tries to quantize gravity using the standard tools of quantum field theory by finding a special point in the space of theories where the infinities cancel. There is causal set theory, which treats spacetime as a discrete set of points with causal relations between them. Each approach has its strengths and weaknesses, and each has its advocates. The challenge for all of these programs is the same: how do you test them? Quantum gravity effects are expected to be important at the Planck scale, and we cannot probe the Planck scale directly. The energy is too high, the distance is too small, so we have to look for indirect signatures. One possibility is gravitational waves. The collision of black holes or neutron stars produces gravitational waves that we can now detect with observatories like LIGO and Virgo. If quantum gravity affects the way gravitational waves propagate, we might see deviations from the predictions of general relativity. So far, no such deviations have been found, but the measurements are getting more precise with every detection. Another possibility is the cosmic microwave background. Quantum gravity effects in the very early universe, during the Planck epoch or the inflationary period, might leave imprints on the CMB. Tiny deviations from the predictions of inflation, subtle patterns in the polarization of the light, could be signatures of quantum space-time. Again, no such signatures have been found yet, but the search continues. Black holes are another promising testing ground. Black holes are places where space-time is extremely curved, where the predictions of general relativity are pushed to their limits. The event horizon, the boundary around a black hole beyond which nothing can escape, is a place where quantum effects should matter. Stephen Hawking showed in the 1970s that black holes are not completely black. They emit radiation, now called Hawking radiation, because of quantum effects near the horizon. Virtual particles pop into existence just outside the horizon, and one of them can escape while the other falls in, giving the appearance that the black hole is radiating. This is a quantum gravity effect, and it is one of the few we can calculate. The problem is that Hawking radiation is incredibly faint for any black hole we know about. The temperature of the radiation is inversely proportional to the mass of the black hole. For a solar mass black hole, the temperature is about 1/1000th of a degree above absolute zero, far too cold to detect against the background radiation of the universe. For a black hole to have a temperature high enough to be detectable, it would have to be tiny, about the mass of a mountain but the size of an atom. And we have no idea if such black holes exist. There is another puzzle related to black holes that quantum gravity might solve. It is called the information paradox. When something falls into a black hole, it disappears from the universe. Or at least, it disappears from our perspective. We cannot see inside the event horizon, but quantum mechanics says that information cannot be destroyed. The state of a system today is determined by its state in the past, and that connection should be reversible. If you know the state of the universe now, you should, in principle, be able to calculate what it was before. But if information falls into a black hole, and the black hole eventually evaporates through Hawking radiation, where does the information go? Hawking radiation is thermal, which means it is random. It does not carry any information about what fell into the black hole, so it looks like information is being destroyed, which violates quantum mechanics. This is the paradox. Physicists have been arguing about the information paradox for decades. Some say the information is encoded in subtle correlations in the Hawking radiation that we just have not figured out how to calculate yet. Others say the information is stored on the event horizon, in a kind of holographic encoding where the three-dimensional information inside the black hole is represented on the two-dimensional surface of the horizon. This is called the holographic principle, and it has become one of the central ideas in quantum gravity. The principle says that the amount of information in a region of space is proportional not to the volume of that region, but to the area of its boundary. This is a strange and counterintuitive idea, but it shows up in both string theory and LQG. It might be a deep clue about the nature of space-time, or it might be a red herring. Nobody knows yet. The information paradox is important because it is a place where quantum mechanics and general relativity clash. Black holes are described by general relativity. Information conservation is a principle of quantum mechanics. If the paradox is real, one of those theories is wrong or incomplete. Most physicists think the answer will come from quantum gravity. A complete theory that unifies the two frameworks should resolve the paradox and tell us what happens to information inside a black hole. String theory has made some progress on this, showing that in certain simplified models, information is not lost. LQG has also made some progress, suggesting that the singularity at the center of a black hole is resolved by quantum effects, which could allow information to escape in some way. But neither theory has a complete answer yet. The difficulty of testing quantum gravity is one reason the field has moved slowly. Progress is being made, but it is progress in mathematics and conceptual understanding, not in direct experimental confirmation. Physicists are building models, calculating properties of quantum spacetime, exploring the structure of the theories, but they do not have the luxury that particle physicists have, the ability to build a bigger accelerator and see what happens. The Planck scale is out of reach. And that means the field relies heavily on consistency checks, mathematical beauty, and indirect evidence. Some people are uncomfortable with this. They argue that without direct experimental tests, quantum gravity is not really physics. It is mathematics, or philosophy, or speculation. Theories need to make predictions that can be checked. If you cannot check them, you're just playing with equations. This is a fair criticism, and it is one that the quantum gravity community takes seriously. But it is also a bit unfair. The lack of direct tests does not mean the questions are not worth asking. Understanding the fundamental nature of space-time, resolving the singularities at the beginning of the universe, and inside black holes, unifying the forces of nature, these are legitimate scientific goals even if the path to achieving them is long and indirect. And there are reasons to be optimistic. The tools are getting better. Gravitational wave astronomy is in its infancy, and as the detectors improve, we will be able to see deeper into the structure of black holes and neutron stars. Future space-based observatories might detect gravitational waves from the early universe, from the inflationary period, or even the Planck epoch. Those waves would carry information about the quantum nature of spacetime, information we cannot get any other way. The cosmic microwave background is being mapped with ever greater precision. Future satellites and ground-based telescopes will measure the polarization of the CMB light at finer scales, looking for the imprint of quantum gravity effects, and theoretical developments are accelerating. String theory and loop quantum gravity are both evolving, refining their predictions, addressing their weaknesses. One of the most exciting recent developments in string theory is the idea of holography, which we mentioned briefly. The holographic principle says that the information in a volume of space can be encoded on the boundary of that volume. String theory gives a concrete realization of this in something called the ADAS-CFT correspondence. This is a mathematical relationship between a theory of gravity in a curved space, called anti-de Sitter space, and a quantum field theory without gravity living on the boundary of that space. The two theories are equivalent, in the sense that any calculation you do in one theory can be translated into a calculation in the other. This is a powerful tool because it allows physicists to study quantum gravity by working with the much simpler quantum field theory on the boundary. It is like having a dictionary that translates a hard problem into an easier one. The ADAS-CFT correspondence is not a complete solution to quantum gravity, because the space it describes, anti-de Sitter space, is not the same as the space we live in. Our universe is expanding and has a positive cosmological constant. AD space is a kind of curved space with a negative cosmological constant, so the correspondence does not directly apply to our universe, but it is a proof of concept. It shows that a theory of quantum gravity can be equivalent to a theory without gravity, that space-time can emerge from more fundamental quantum degrees of freedom, and that is a profound insight. It suggests that space-time is not fundamental, it is emergent, built from something deeper. What that something is, and how it works in a universe like ours, is still an open question. Loop quantum gravity has its own version of holography. In LQG, the area of a surface is quantized, and the quantum numbers on the spin network edges that cross the surface determine the area. The maximum amount of information you can store on that surface is proportional to the area, not the volume. This is the same result as in string theory, arrived at from a completely different starting point. The fact that both approaches give the same answer is encouraging. It suggests that holography is a real feature of quantum gravity, not just an artifact of one particular framework. Another promising direction is the study of quantum cosmology. This is the application of quantum gravity to the universe as a whole. Instead of just asking what happens at the singularity or inside a black hole, you ask what the wave function of the universe is. What does it mean to apply quantum mechanics to the entire cosmos? This is a deep and difficult question, and it touches on some of the philosophical issues we discussed earlier. If the universe is described by a wave function, what does it mean for that wave function to collapse? Who or what is measuring the universe? Or does the wave function never collapse, as in the many worlds interpretation, with the universe constantly branching into multiple copies? Quantum cosmology does not have a complete answer to these questions, but it provides a framework for thinking about them. One of the key ideas is the Wheeler-DeWitt equation, a kind of Schrödinger equation for the wave function of the universe. The equation is hard to solve, and it has some strange features. For one thing, it does not include time explicitly. Time is not a parameter in the Wheeler-DeWitt equation, it is part of the quantum state. This fits with the idea that time is emergent, that it arises from the quantum state of the universe rather than being a fundamental background. But it also makes the equation difficult to interpret. What does it mean for the universe to have a wave function if there is no time to evolve it? Despite these challenges, quantum cosmology has made some progress. The no-boundary proposal, which we mentioned earlier, is one example. Hawking and Hartley suggested that the wave function of the universe is highest for configurations where space-time is smooth and finite, with no sharp boundary at the beginning. The universe does not start at a singularity. It starts in a kind of fuzzy quantum state where the distinction between time and space is blurred. As the universe evolves, time emerges, and the familiar classical space-time of general relativity takes shape. This is a speculative idea, but it is grounded in the mathematics of quantum gravity, and it provides a way of thinking about the origin of the universe without requiring a cause or a beginning in the traditional sense. Loop quantum cosmology, the application of LQG to cosmology, has also made progress. As mentioned, LQC predicts that the Big Bang singularity is replaced by a bounce. The universe contracts, reaches a maximum density, and then bounces back into an expanding phase. The bounce is not a violent singular event, it is a smooth transition, governed by the quantum geometry of the spin network. This has been worked out in detail for simple cosmological models, and the results are encouraging. If quantum gravity effects are only important at the Planck scale, and if the Planck scale is forever out of reach, then the theory might be untestable in any direct sense. But there is hope. The inflationary period, which we know happened, occurred just after the Planck epoch. Inflation stretched tiny quantum fluctuations to macroscopic scales, and those fluctuations are imprinted on the cosmic microwave background. If quantum gravity modifies the behavior of those fluctuations in some way, if it leaves a subtle signature in the pattern of the CMB, then we might be able to test quantum gravity indirectly by measuring that signature. Several groups are working on this, calculating what the CMB should look like if spacetime is discrete, or if there are extra dimensions, or if the bounce happened. So far the results are inconclusive, but the search continues. String theory has another possible signature, the existence of extra dimensions. If the extra dimensions are compactified at a scale not too far below the Planck scale, they might have effects that we could detect. Gravity might behave differently at very short distances, or particles might have unexpected properties due to interactions with the extra dimensions. Some string theory models predict that black holes at the Large Hadron Collider could produce micro-black holes if the extra dimensions are large enough. No such black holes have been seen, which puts constraints on the size of the extra dimensions, but it does not rule them out. They could be smaller than the energies we can probe, or they could be configured in a way that makes them hard to detect. The challenge is that both string theory and loop quantum gravity are still incomplete. Neither has a full, worked-out description of how the theory reproduces the world we see at low energies. String theory has the landscape problem, the vast number of possible vacua, and no clear way to pick out the one that describes our universe. Loop quantum gravity has the semi-classical limit problem, the difficulty of showing that smooth spacetime emerges from the quantum network at large scales. Both programs are making progress, but both still have a long way to go. And that brings us to the humbling conclusion. After a century of effort, after thousands of papers and decades of work by some of the smartest people on the planet, we still do not have a theory of quantum gravity. We have candidates, we have frameworks, we have ideas that look promising, but we do not have the answer. The problem is hard. It is harder than almost any other problem in physics, and it might take another century to solve, or it might be solved tomorrow by someone who sees something everyone else has missed. What is clear is that the quest for quantum gravity is not just about equations and calculations. It is about understanding the most fundamental aspects of reality. What is space-time? Is it continuous or discrete? Is it fundamental or emergent? What happens at the singularity? Does time have a beginning? These are not abstract questions. They are questions about the universe we live in, the universe that started nearly 14 billion years ago in a moment we call the Big Bang. And until we have a theory of quantum gravity, we cannot fully answer them. The singularity is still a wall, the Planck epoch is still a mystery. And the question of what caused the Big Bang, or whether it even makes sense to ask that question, remains open. But the search continues. Physicists are working on it right now in universities and institutes around the world. They are writing equations, running simulations, building models, testing ideas. Some of them will turn out to be wrong, some of them might be right. And one of them eventually might crack the problem, might find the theory that unifies general relativity and quantum mechanics, that resolves the singularity, that tells us what space-time really is at its deepest level. That theory, when it comes, will be one of the great achievements of human thought. It will reshape our understanding of the universe. It will answer questions we have been asking since the dawn of science, and it will open up new questions, deeper ones, stranger ones, questions we have not even thought to ask yet. Because that is how science works. Every answer leads to a new question. Every door you open reveals another door behind it. And the quest to understand where we came from, what started the Big Bang, what happened before time began, is a quest that might never fully end. But the journey itself, the effort to push past the walls and see what lies beyond, that journey is what defines us. It is what makes us human, and it is a journey that is far from over. The search continues. Physicists are working on it right now in universities and institutes around the world. They are writing equations, running simulations, building models, testing ideas. Some of them will turn out to be wrong, some of them might be right, and one of them eventually might crack the problem. Might find the theory that unifies general relativity and quantum mechanics, that resolves the singularity, that tells us what space-time really is at its deepest level. That theory, when it comes, will be one of the great achievements of human thought. It will reshape our understanding of the universe. It will answer questions we have been asking since the dawn of science. And it will open up new questions, deeper ones, stranger ones, questions we have not even thought to ask yet. Because that is how science works. Every answer leads to a new question. Every door you open reveals another door behind it. And the quest to understand where we came from, what started the Big Bang, what happened before time began, is a quest that might never fully end. But the journey itself, the effort to push past the walls and see what lies beyond, that journey is what defines us. It is what makes us human, and it is a journey that is far from over. So where are we? After everything we have covered, after walking through singularities and inflation and quantum fluctuations and bouncing universes and multiverses and the hunt for quantum gravity, where does that leave us? What can we actually say, with confidence, about what caused the Big Bang? The honest answer is not much. We can describe what happened after the Big Bang with extraordinary precision. We can trace the evolution of the universe from the first fraction of a second onward. We can measure the temperature of the early universe, the density of matter and radiation, the rate of expansion. We can watch how atoms formed, how stars ignited, how galaxies assembled themselves into the vast cosmic web we see today. The Big Bang Theory, as a description of the early universe's expansion and cooling, is one of the most successful scientific theories ever developed. The evidence supporting it is overwhelming. The cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, the redshift of distant light, all of it points to the same conclusion. The universe was once much smaller, much hotter, much denser, and it has been expanding and cooling ever since. But the theory does not tell us what caused the expansion to start. It does not explain where the universe came from. It does not answer the question of why there is something rather than nothing. And after more than a century of work by some of the brightest minds humanity has ever produced, we still do not have a definitive answer to those questions. We have ideas, we have frameworks, We have models that look promising and make interesting predictions, but we do not have the answer. NASA, in its educational materials on the Big Bang, puts it plainly. We do not know what triggered that initial rapid expansion. The most fundamental question about the origin of the universe remains unanswered. Live science, summarizing the state of the field, is even more blunt. Short answer, we do not know. The question of what came before the Big Bang, or what caused it, is one of the great open problems in physics. It is not a problem we are ignoring or avoiding. It is a problem we are actively working on. It is just a really, really hard problem. Part of the difficulty is conceptual. If time itself began at the Big Bang, then asking what came before is like asking what is north of the North Pole. The question assumes a framework, a direction, a concept of before that does not apply. You can walk north from anywhere on Earth except the North Pole. At the North Pole, north stops having meaning. Every direction is south. The same thing might be true for time. At the Big Bang, time starts. Every moment is after. There is no before because before requires time, and time had not started yet. This is not just a clever wordplay. It is a real issue that comes from taking general relativity seriously. In Einstein's theory, time is part of space-time, and space-time is a dynamical entity that can stretch and curve and in principle begin. If space-time began at the Big Bang, then time did too, and if time began, the concept of causality, of one event leading to another, might not apply to the beginning itself. This is deeply unsatisfying. Our brains are not built to accept that something can just happen without a cause. We are wired to look for explanations, for chains of events, for reasons. A ball rolls because you pushed it. Water boils because you heated it. The universe expands because, well, something must have started it, except that something might not exist. The expansion might not have a cause in the traditional sense. It might just be the way the universe is, the way it has always been, with no deeper explanation available. Or maybe not. Maybe there is a deeper explanation, and we just have not found it yet. That is what drives the research. Physicists are not content to shrug and say it just is. They want to know. They want to find the mechanism, the cause, the reason. And so they keep working, building models, testing ideas, pushing the boundaries of what we understand about space and time and matter and energy. Let's recap what we have covered, because the landscape of ideas is vast and it is easy to get lost in it. We started with the singularity, the point where general relativity predicts infinite density and temperature, and where the equations break down. The singularity is not a place or a thing. It is a mathematical artifact, a sign that our theory is incomplete. General relativity works beautifully at describing the expansion of the universe, but it cannot describe the moment of the Big Bang itself. For that, you need quantum gravity, a theory that unifies general relativity with quantum mechanics, and we do not have one yet. Then we talked about inflation, the brief period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. Inflation solves several major problems in cosmology. It explains why the universe is so flat, why it is so smooth, why the cosmic microwave background looks the same in every direction. It also provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies. Inflation is supported by strong evidence, and it is the leading framework for understanding the early universe. But inflation does not explain what caused the Big Bang. It explains what happened immediately after, but it does not tell you why there was something to inflate in the first place. It pushes the question back one step without fully answering it. Next, we looked at quantum fluctuations, the idea that the structure of the universe might have originated from random variations in quantum fields during inflation. This is one of the great insights of modern cosmology. The largest structures in the universe, galaxy clusters spanning hundreds of millions of light years, trace back to quantum blips that existed for less than a billionth of a trillionth of a trillionth of a second. Those blips were stretched by inflation and became the seeds for everything we see. But quantum fluctuations still require a quantum field to fluctuate, and they require the laws of quantum mechanics to govern how the fluctuations behave. So even if the universe emerged from a quantum fluctuation, you have not explained where the field came from or why the laws are what they are. Then we explored pre-Big Bang cosmologies, the idea that the Big Bang was not the beginning, but a transition from a previous state. Bouncing cosmologies propose that the universe contracted, reached a minimum size, and then bounced into the expanding phase we observe today. Cyclic models propose an infinite series of expansions and contractions, each cycle lasting trillions of years, with no first cycle and no final one. These ideas are grounded in frameworks like loop quantum gravity and string theory, and they avoid the singularity by replacing it with a smooth quantum transition. But they do not answer the ultimate question, they just push it back further. If the universe is cyclic, why is it cycling? If it bounced, what sustained the bounce? You still do not have a first cause or a final explanation. We also talked about the multiverse, the idea that our universe is just one bubble in a vast, possibly infinite collection of universes. The level 1 multiverse is the simplest version, where space is infinite and every possible configuration of matter eventually repeats. The level 2 multiverse comes from eternal inflation, where different bubbles settle into different vacua with different laws of physics. The level 3 multiverse comes from the many worlds interpretation of quantum mechanics, where the universe constantly branches into parallel copies. And the level 4 multiverse, the most speculative, proposes that every mathematically consistent structure is a real universe. The multiverse offers a potential explanation for the fine-tuning of the constants, but it is controversial because it is hard to test. If other universes are forever beyond our reach, how can we ever know they exist? And even if the multiverse is real, it does not explain why there is a multiverse in the first place. It just replaces the question of why our universe exists with the question of why the multiverse exists. Finally, we dug into quantum gravity, the search for a theory that unifies general relativity and quantum mechanics. String theory proposes that particles are tiny vibrating strings and that space-time has extra dimensions. Loop quantum gravity proposes that space-time is made of discrete quantum chunks, a network of connections rather than a smooth fabric. Both approaches are incomplete, both have problems. But both are serious attempts to solve the singularity problem and describe the Planck epoch, the first 10 to the negative 43 seconds after the Big Bang. If and when we have a working theory of quantum gravity, it will revolutionize our understanding of space-time, black holes, and the origin of the universe. But even then, it might not answer the ultimate question. It might tell us what the universe was like at the very beginning, but it might not tell us why there was a beginning at all. So after all that, we are left with a collection of ideas, none of them proven, none of them complete, all of them pointing in different directions. Some physicists think the universe emerged from a quantum fluctuation. Others think it bounced from a previous contracting phase. Some think it is part of an eternal multiverse. Others think the question of what came before is meaningless because time itself began at the Big Bang. And all of them are working with incomplete theories, trying to fill in the gaps, trying to find the missing pieces that will finally give us the answer. This is frustrating. It is also beautiful, because what we are witnessing is science at its most honest. Science does not pretend to have all the answers. It does not claim certainty where there is none. It follows the evidence, builds models, tests predictions, and admits when it does not know something. The question of what caused the Big Bang is a perfect example of this. We do not know. We have ideas, but we do not know. And instead of making up an answer or giving up, we keep working, we keep asking, we keep pushing. The process is slow, it is messy. It involves a lot of trial and error, a lot of wrong turns, a lot of ideas that seem promising at first and then turn out not to work. But that is how progress happens. You try something, you see if it works. If it does not, you try something else. String theory has been around for more than 40 years, and it still has not made a confirmed prediction about the real world. Loop quantum gravity has made progress on the singularity problem, but it has not yet shown that it reproduces general relativity at large scales. Inflation is supported by strong evidence, but we still do not know what the inflaton field is or what started it. Every framework has its strengths and its weaknesses, and none of them are complete. This is the reality of cutting-edge science. You're working at the edge of what is known, trying to push into the unknown. You do not have a clear path. You do not have a manual. You're figuring it out as you go, and most of the time you are wrong. But every failure, every wrong idea, every model that does not work teaches you something. It narrows the space of possibilities. It tells you where not to look, which is almost as valuable as knowing where to look. And occasionally, very occasionally, someone has an insight that changes everything. A new idea, a new framework, A new way of looking at the data that suddenly makes sense of things that were confusing before. That is when breakthroughs happen. Not through steady, predictable progress, but through sudden leaps that no one saw coming. The history of cosmology is full of these moments. The discovery that the universe is expanding was a shock. It overturned the assumption that the cosmos was eternal and unchanging. The realization that the expansion is accelerating, driven by dark energy, was another shock. Nobody expected it. The discovery of the cosmic microwave background in 1965 was accidental, the result of two engineers trying to get rid of noise in a radio antenna. They thought it was pigeon droppings. It turned out to be the echo of the Big Bang. The development of inflation in the early 1980s solved problems that had seemed insurmountable. The realization that string theory includes gravity was a surprise that turned a failed theory of the strong force into a candidate for a theory of everything. Science is full of these moments, and there is no reason to think we have had the last one. So maybe the answer to what caused the Big Bang is just around the corner. Maybe someone working in a lab right now is about to have the insight that cracks the problem. Maybe a graduate student is running a simulation that will reveal a new pattern in the data. Maybe a theorist is scribbling equations on a blackboard and is about to notice something that everyone else has missed. It has happened before. It will happen again. Or maybe not. Maybe the problem is harder than we think. Maybe it will take another century. Maybe it will take longer. Maybe we will never know. And here is the thing. That is okay. The fact that we do not have the answer does not diminish the effort. The fact that the question is hard does not make it less worth asking. The opposite is true. The hardest questions are the ones most worth pursuing, because they are the ones that push us the furthest, that force us to develop new tools and new ways of thinking, that expand the boundaries of what we understand about reality. The quest to understand the origin of the universe is not just about finding an answer, it is about the journey. It is about the process of asking, of wondering, of refusing to accept ignorance as the final state. This is what makes us human. Not the answers we have found, but the questions we keep asking. Every other species on this planet lives in the present. They eat, they sleep, they reproduce, they survive. They do not wonder where they came from or why they are here or what it all means. They just are. Humans are different. We look up at the night sky and we ask why. We see the stars and we want to know what they are made of and how far away they are and how old they are and where they came from. We see the galaxies and we want to know how they formed and where they are going and what will happen to them in the end. We ask questions that have no immediate survival value, no practical application, no payoff beyond the satisfaction of knowing. And we do it anyway. We do it because we cannot help ourselves. We do it because we are built to ask. The question of what caused the Big Bang is one of the deepest questions we have ever asked. It is a question about the origin of everything, about why there is something rather than nothing, about the nature of time and space and existence itself. It is a question that touches on philosophy, theology, mathematics, physics, cosmology. It is a question that has occupied thinkers for thousands of years, from ancient creation myths to modern scientific theories. And it is a question we still do not have a complete answer to. But that is not a failure. It is a testament to the depth of the mystery. The universe is under no obligation to make sense to us. It is under no obligation to reveal its secrets. The fact that we have come as far as we have, that we can trace the history of the cosmos back to the first fraction of a second, that we can measure the temperature of the early universe and the density of matter and the age of the oldest stars, all of that is astonishing. We are a species that evolved on a small planet orbiting an average star in an average galaxy, and we have figured out how old the universe is. We have mapped the large-scale structure of space. We have detected gravitational waves from colliding black holes billions of light years away. We have photographed the event horizon of a supermassive black hole at the centre of a distant galaxy. We have measured the cosmic microwave background to 1 part in 100,000. These are extraordinary achievements. They are achievements that no other species on this planet could have made, because no other species asked the questions that lead to them. And we are not done. We are still asking. We are still building telescopes, launching satellites, designing experiments, writing equations. We are still trying to understand. The James Webb Space Telescope is giving us the deepest view of the universe we have ever had, looking back to when the first galaxies were forming, just a few 100 million years after the Big Bang. Gravitational wave observatories are opening a new window on the cosmos, allowing us to detect events that are invisible to traditional telescopes. Future missions will map the cosmic microwave background with even greater precision, searching for subtle signatures of quantum gravity or inflation, or the multiverse. Particle accelerators are being upgraded, pushing to higher energies, looking for new particles and new forces that might give us clues about the fundamental structure of reality. The tools are getting better, the data is getting richer. The theories are getting more refined, and the questions are getting sharper. We are not just asking what caused the Big Bang anymore. We are asking whether the question even makes sense. We are asking whether time is fundamental or emergent. We are asking whether space-time is continuous or discrete. We are asking whether our universe is the only one or one of many. We are asking whether the laws of physics are fixed or variable. These are not simple questions with simple answers. They are deep, complex, multifaceted questions that require new ways of thinking and new frameworks for understanding. And that is exciting because every time we refine a question, we get closer to an answer. Every time we realize that a question does not make sense in the way we thought it did, we learn something important. The fact that asking what came before the Big Bang might be like asking what is north of the North Pole is not a dead end. It is a clue. It tells us something about the nature of time, about the structure of space-time, about the limits of causality. It forces us to think more carefully about what we mean by before and after and cause and effect. It pushes us to develop new concepts, new language, new mathematics. This is how science progresses, not in a straight line from ignorance to knowledge, but in a winding path with detours and backtracking and sudden leaps forward. You try something. It does not work. You try something else. That does not work either. You go back to the drawing board. You rethink your assumptions. You look at the problem from a different angle. And then maybe you see something you did not see before. A connection, a pattern, an insight. And that insight opens up a new direction, a new line of inquiry, a new set of questions. The quest to understand the origin of the universe has followed this path. In the 1920s, we did not even know the universe was expanding. We thought the Milky Way was the entire cosmos. Then Hubble measured the redshifts of distant galaxies and everything changed. We realized the universe is much larger than we thought, and it is growing. That raised the question of where the expansion came from. Lemaitre proposed that the universe started from a primeval atom, a concentrated state that exploded and expanded. That was the beginning of the Big Bang theory, though the name was originally meant as a dismissive joke. Over the next few decades, the theory was refined, tested, and confirmed. The discovery of the cosmic microwave background in 1965 was the smoking gun. The universe really did start from a hot, dense state. That was no longer a hypothesis, it was a fact. But facts raise new questions. If the universe started from a hot, dense state, where did that state come from? What caused it? What was there before? These questions pushed cosmologists to develop inflation, to explore quantum gravity, to think about bouncing universes and multiverses and the emergence of time. And each new idea, each new framework has opened up new questions. We're further from the beginning of the journey than we were a century ago, but we're also deeper into the mystery. We know more, but we also know how much more there is to know. And that is the beauty of it. The universe is not a simple place. It is not a puzzle with a single solution that you find and then you are done. It is a layered, complex, endlessly surprising reality that reveals new depths every time you look closer. The more we learn, the more we realize how much we do not know. And that realization, instead of being discouraging, is inspiring. Because it means there is always more to discover. There is always another question to ask. There is always another mystery waiting. The drive to know is not universal. Most people go through life without wondering about the origin of the universe. They have other concerns, other priorities, other ways of finding meaning and purpose, and that is fine. But there are some people, a small fraction of humanity, who cannot help but ask, who look at the night sky and feel a pull, a need to understand, to know, to figure it out. These are the people who become scientists, who dedicate their lives to answering questions that most people never think to ask. They do it not because it is easy, not because it is profitable, not because it will make them famous, though occasionally it does. They do it because they are compelled to, because the questions are there, unanswered, and they cannot rest until they have at least tried to find the answers. This is the human drive to know. It is the impulse that built the pyramids and the Great Wall, that mapped the continents and the oceans, that split the atom and decoded the genome. It is the impulse that put footprints on the moon and rovers on Mars. It is the impulse that built the Large Hadron Collider and the Hubble Space Telescope and the James Webb Space Telescope. It is the impulse that drives cosmologists to spend their entire careers studying the first fraction of a second after the Big Bang, a moment so brief and so remote that it barely registers as real. And it is the impulse that will eventually, if we are lucky and if we keep at it, give us the answer to what caused the Big Bang, or at least get us closer. The universe does not care whether we understand it. It existed for more than 13 billion years before we showed up, and it will exist for trillions of years after we're gone. The stars will keep shining, the galaxies will keep spinning, the expansion will keep accelerating, whether or not we figure out where it all came from. Our understanding or lack of understanding makes no difference to the cosmos, but it makes a difference to us. It matters to us. Because understanding is what we do. It is how we make sense of the world. It is how we find meaning in the chaos. We are meaning-making creatures, and the biggest, deepest, most profound meaning we can find is in the structure of reality itself. And so we ask. We ask what caused the Big Bang. We ask what came before. We ask why there is something rather than nothing. We ask what time is, what space is, what matter is, what energy is. We ask how the universe began and how it will end. We ask whether we are alone or whether there are other intelligences out there, asking the same questions. We ask whether the laws of physics are the only laws or whether there are other universes with other laws. We ask whether reality is fundamentally deterministic or probabilistic, continuous or discrete, finite or infinite. We ask because we can. We ask because we must. The fact that we do not have all the answers yet is not a reason to stop asking. It is a reason to keep going. Every unanswered question is an invitation. Every mystery is a challenge. The universe is full of puzzles, and some of them are harder than others. The origin of the universe is one of the hardest, maybe the hardest, but that is what makes it worth pursuing. Because if we can crack it, if we can figure out what caused the Big Bang, we will have done something extraordinary. We will have traced the chain of causation back to the very beginning, or as close to the beginning as it is possible to get. We will have answered the oldest question humans have ever asked. Where did all of this come from? And even if we never get a complete answer, even if the question turns out to be unanswerable in some deep sense, the effort will still have been worth it. Because the process of trying to answer the question has already taught us so much. It has given us general relativity and quantum mechanics, two of the most successful theories in the history of science. It has given us the Big Bang theory, a framework that explains the history of the cosmos with remarkable accuracy. It has given us inflation, which solves some of the deepest puzzles in cosmology. It has given us the multiverse, a provocative idea that challenges our assumptions about the uniqueness of our universe. It has given us string theory and loop quantum gravity, ambitious attempts to unify the forces of nature and describe the fundamental structure of space-time. All of this came from asking what caused the Big Bang. All of this came from refusing to accept ignorance as the final answer. So where does that leave us? Here, now. In a universe that is 13.8 billion years old, give or take a few tens of millions of years. A universe that started from an unimaginably hot, dense state, and has been expanding and cooling ever since. A universe that is full of galaxies and stars and planets, at least one of which produced a species capable of asking where it all came from. A universe that might be the only one, or might be one of infinitely many. A universe that might have had a beginning, or might have been cycling forever. A universe that might have been caused by a quantum fluctuation, or a collision of brains, or a bounce from a previous phase, or something we have not thought of yet. A universe that, for all its mysteries, is knowable, at least partly, at least in principle. We do not know what caused the Big Bang. We do not know what came before. We do not know whether before is even a meaningful concept, but we know more than we did a century ago. We know more than we did a decade ago. We are learning slowly, painstakingly, one discovery at a time. And as long as we keep asking, as long as we keep pushing, as long as we refuse to accept that some questions are too big or too hard or too strange to answer, we will keep making progress. We will keep moving forward, We will keep uncovering the secrets of the cosmos, one layer at a time, one mystery at a time. The universe is not going to hand us the answers. We have to work for them. We have to build the telescopes and design the experiments and write the equations and test the predictions. We have to be wrong 1,000 times before we are right once. We have to be patient and persistent and willing to follow the evidence wherever it leads, even if it leads to places we did not expect, even if it forces us to rethink everything we thought we knew. That is the price of understanding. That is the cost of knowledge, and it is a price worth paying. Because in the end, the question of what caused the Big Bang is not just a question about the universe. It is a question about us, about who we are, about what we are capable of, about what it means to be a conscious, curious creature in a vast and ancient cosmos. We are the universe trying to understand itself. We are the cosmos waking up, looking around and asking how it got here. And that is remarkable. That is special. That is something worth celebrating, even if we never get the final answer. The journey is what matters. The quest is what defines us. The fact that we are asking at all, the fact that we are capable of asking, the fact that we care enough to spend our lives searching for answers to questions that have no immediate practical value, that is what makes us human. That is what separates us from the rocks and the rivers and the trees. We are not content to simply exist. We want to know why. We want to understand. We want to see the whole picture, even if the picture is so big that we can only ever see a tiny corner of it. 13.8 billion years ago, something happened. The universe, as we know it, began. Space started expanding. Time started ticking. Matter and energy burst into existence and began the long, slow process of cooling and condensing and organizing into stars and galaxies and planets and people. We do not know why it happened. We do not know what caused it. We do not know whether it was the first time or just the latest in an infinite series. But we know it happened, and we are still here, still asking, still searching, still refusing to give up on the possibility that one day somehow we might figure it out. That is the human drive to know. That is the thing that pushes us forward, that makes us climb mountains and cross oceans and build machines that can see to the edge of the observable universe. That is the thing that makes us ask what caused the Big Bang, even when we know the answer might be forever out of reach. Because the asking is the point. The searching is the point. The refusal to stop wondering, the refusal to accept mystery as the final word, that is what defines us. That is what makes us who we are. And maybe, just maybe, that is enough. So here we are, 13.8 billion years after the moment that started everything, sitting on a small planet orbiting an average star in an unremarkable galaxy, asking a question that might not have an answer. What caused the Big Bang? We have traced the universe back to the first fraction of a second. We have measured its temperature, its density, its rate of expansion. We have built models that describe how particles formed, how atoms assembled, how stars ignited, how galaxies clustered into the vast cosmic web we see today. And every step backward through time, every refinement of our understanding, has brought us closer to the edge, closer to the wall, closer to the moment where our equations break down and our language stops working, and the concept of before loses all meaning. And standing at that edge, after walking through singularities and quantum foam and bouncing universes and multiverses and the hunt for quantum gravity, the most honest answer we can give is this: we do not know, not yet, maybe not ever. The question might be unanswerable. Time itself might have started at the Big Bang, rendering the idea of a cause meaningless. Or the answer might be hiding just beyond the reach of our current theories, waiting for the next Einstein, the next breakthrough, the next leap in understanding that no one saw coming. But here is what matters: the fact that we are asking at all, the fact that a species of curious primates evolved the ability to look up at the night sky and wonder where it came from, the fact that we refuse to accept ignorance as the final state. We do not know what caused the Big Bang, but we know we want to know. And that drive, that refusal to stop asking, that insistence on pushing past every wall we encounter, that is not a failure. That is the whole point. We are the universe trying to understand itself. And whether or not we ever find the answer, the search is what makes us human.